I'll just show you how to create. First, we'll go with the creation of a rectangle. Okay, and we are assuming the cross section is 50 by 50. Okay, so I'll edit this 50 using dimensions.
Yes, parody, toted like a prodigy.
One side is modified, then once again dimensions and other side. And change it to 50. Now from here, you can move your screen or zoom in, zoom out, and you need to move on to 3D mode so that you can convert your surface body to a solid body. So you can see the arrow direction. You can drag it towards that direction and specify it to be 1000. Okay, so this is the length. Now with this, we'll come up with the dimensions, that is cross section 50 by 50, and we are assuming a length of 1000. So one 3D geometry is ready. So let's understand how to work with the flow. So we'll open workbench. Meanwhile, let me just save this geometry. Say save as, and you can specify it the name. Okay, so my workbench is open, and you have a predefined structure. I told you, right, that any type of analysis you want to do, let it be a structural, let it be thermal, either steady state or transient state, or you're working on any other physics, whatever is the physics, the analysis, a predefined structure is already existing. So out of that, first we'll start with taking with a static structural. Okay, and in that, all the detailed explanation and all ma'am will continue, but now we will understand how to work on this 1D, 2D and 3D whenever we are converting your geometry from 3D to either 2D or 1D. So in that condition, can we use the results that we are getting for 2D to use it in case of a 3D, or when we are converting our geometry from 3D to 1D, can we use it also to give the results for a 3D condition, right? So we'll just follow same dimension, same length, same boundary condition, and solving using this for three conditions. So this is my 3D condition where I'm solving. So 3D, and now I need to add my geometry. So click on geometry, import geometry, and wherever you have saved, you can take browse the location. Once you get a green check, you are ready to proceed for next step. So now we'll open our model window where all the you can say meshing related, or you defining some boundary condition, working with the connections, post processing, all that you can do in the single window, right? So this is our geometry. Let's say you are already having idea of working with uh, meshing, right? So I'll go with the default meshing here, or you can add some sizing control to your geometry. Once you are done with the meshing, since this is a simple geometry, we don't have to work more on checking with the quality and all. So even by default, whatever mesh it is generated, even if you want to check the quality, it's going to be almost the required quality. Like when we say zero point 0.7 to 1 range, so we are getting at a range of 0.75, which is absolutely fine for us to proceed. Okay, so now as we consider a cantilever beam condition, one side we have to fix it, and the other side we have to apply a load. So we have some detections which you can detect, like you can go for your vertex selection, edge selection, surface selection, body selection, and also you have node selections and element, particular surface of an element you can select, or complete element you can select. So these conditions will help you out when you're working with the nodal conditions. So as of now, we are dealing with direct solid, so we don't need these things to check now. So let me take a surface selection. So I have selected this surface, and whatever boundary conditions I have to apply. Let's say I not only fixing a condition, any other boundary conditions. So related to structural problem, whatever are available, you will get a list of those boundary conditions here. Okay, so for me, I need the fixed support. So I'll take fixed support. That is constraining it from all 6 degrees of freedom. Then in the opposite side, we have to give a downward load so that it's working as per a cantilever condition, right? So we'll go with insert and add a force. So now I'll take this edge selection and try to give the downward loading. Now you can see this global axis, right? So for this global axis to have a downward loading, I need to apply in particular XYZ direction, right? So that component I need to select, or else I can also define direct magnitude value, which will you don't have to select your which axis you want to specify. But I want it in a downward direction and I don't have a magnitude value, so I'll just go with changing from vector to components. Now, to have a downward one, I need to have a negative downward loading with a value of, let's say, 100 Newton. I apply a load here. Okay, so before that, make sure now you have your units properly set here. So if you are having some change in the units, anytime you are working, just check with your units once. Okay, and then since our simple beam condition is already ready, and in case of when we are solving a 1D body, we cannot find the stress for a line body. So that's how, like, for comparison purpose, we'll only check with the deformation in all three conditions. So we'll go to solution and insert solution and total deformation. Now here I'm adding total deformation, where, like, if, as per your requirement, you can switch on to directional deformation, in particular XYZ direction. And now say this to solve, right? So I hope by now you have understood how to work with the flow, right? So first you have checked out, like, you have imported your geometry, and make sure you do not have any question mark there. So basically, if you get question mark, either there is some problem with your geometry, or you can say there is some surface existing. So in that condition, it will show you an indication of some surface. If you are importing, a thickness would be required to specify. Okay, so that indication with an yellow color notation you will be able to see. Then next is, now when I solved this problem, it was done with a default material, that is static structure, structural steel material is being used here, right? Then we have seen yesterday how to create a global coordinate, right? For a component based on selection of geometry particular component, we have seen how to create a coordinate. Now in further sessions, maybe you'll get an exposure towards using coordinate to also define your boundary condition, or else, like, you mostly for meshing purpose, for adding sphere of influence, you can use this global coordinates, or working with your joints, you can use coordinate system. Okay, then next you have is the mesh condition, which you have already seen the elaborated procedure, how to get how to work with the different method, why we should first of all mesh our geometry, in how to get a good quality of elements, which is a suitable meshing method based on your geometry, and based on type, like, you can say based on intricate structure also, like which method should be opted. Then next you have seen static structural, where analysis settings you are seeing, where basically you are going to see what is the time step it is going to continue. Like for when we say static structural, we solve it for 1 second. Or when we solve it for other conditions, transient conditions, so there we have to specify number of steps and what are the sub steps, and also that is further when you explore you will be able to understand. Then we have also seen how to add a support. So similar way, loads and support, you have to go insert, and based on your problem statement, you need to specify the boundary conditions. Later comes out what solutions you are looking for. So as I told, I want to do a comparison test between 1D, 2D, 3D. Am I able to get the similar results in all three conditions. So that's how I can only use deformation, not the stress condition to choose, because uh, for 1D I cannot have a stress, right? Also, I can consider one more thing, that whenever we are, it's obvious that when you work on 3D, you get to have lot of elements getting evolved, right? So there you have statistics where you can see how many elements and nodes are existing. But similar way, when you are working with the 2D and 1D, definitely you are going to reduce your elements. So that is one of the add-on advantage. Like when you are converting, you have to work like you will get reduced mesh and you can solve your problem fastest way, right? So till here I believe everyone have understood how to do the simple procedure. If you want me to repeat the procedure once again, I don't mind, I'll show it to you, and then someone has to project their screen and do and show it to everyone, whoever is a bit getting lagged out or who missed out few steps, they can follow that steps. Yeah, please let me know in the chat box that do you want me to repeat or should we continue further. Fine. So I'll repeat the procedure. Okay. So basically, first I have taken a static structural geometry creation you have already seen. Going back to geometry, and you need to import your geometry. Wherever you have stored your geometry, you can browse the location. Then open your mechanical window. Before that, I'll just close down this entire window and open my mechanical. Okay, so I mean, like it's almost loading the geometry. Yeah, so we have got our geometry. We are proceeding with default material structural steel mesh default. So right click and say generate mesh. Then next you have static structural where you need to specify the boundary condition. So first select one end using surface selection and say static structural, right click, insert and fix support. Okay, then the other side, I'll take this edge. Okay, one of the edge I have selected and I'll apply a downward load here. So go to static structural, insert and say force. Now this force when I'm applying, since I said I want in a like uh, component, separate component, I want to add it like y axis, I want to add the loading condition. So go with components defined by components. Y direction, negative sign you need to keep, and the load of 100 newtons you are applying, so that you are getting a downward load. Arrow must be visible to you so that you get an idea. And in the solution, go to insert and say deformation and total and simply solve. So the comparison thing we will do once we are done with solving all three conditions. But meanwhile, I want all the students now to start doing this job, static structural simple 3D problem, and one by one show it. So you have I 5 minutes of 2D. Okay. So let me just share screen. So for that, no, first we need a 2D geometry. So we'll go with new and create a 2D geometry. Now, since we know that the length was 1000 and a cross section was 50, so I can assume a rectangle and then again add the length as 1000. Okay, and this dimension, I'll make it as 50. Done. So now you can see your 2D sketch is ready. So just go to 3D mode and your surface body will be ready. Now save this as a 2D geometry or some name you can give. Okay, so this is how you are ready with your geometry. And once again, take a static structural. Now name this as 2D. Okay, and import your geometry. Same procedure, geometry, import geometry, and then browse your location. Then you have model and open your mechanical window. Okay, so now when I imported a surface geometry, I get to see question mark in my geometry. That means you are missing out some of input to provide. Okay, so that thickness for what it needs to solve, you have to give. So my thickness was 50, right? So 50 by 50 was my cross section. So I'm adding a thickness of 50 here for the surface body and going with default mesh. Okay, if someone has kept their mic on, please off it. I'm able to hear my own voice. Right, so then next, once again, the same boundary conditions you need to apply. Okay, so for this, we'll go with static structural, insert and say fixed. Now, this time I need to fix my edge. So I'll go with edge selection and click on apply, right? Then next, to apply a downward loading, I'll make use of this vertex selection here and static structural once again and say force. So once again, in my negative y direction, I have to give the loading. Same 100 Newton I'll give. Okay, and then solve it for deformation, right? So I believe till here it is clear, and the procedure also you have seen. Please start.
Hello, ma'am.
Yes,
What is thickness value?
thickness we are giving 50. Has got like example you can consider. Let's design one geometry first to show you how the designing works out. So basically, to create your 1D body, you can create it using two different points and you just create the beam between those using some cross section. Or you can take a line and assign some cross section to that. So these two are the procedures. So let me show you first using a line. So you can take a line and say 1000, same dimension we are using, and now to this line, you can directly assign the cross section, or as I told you, you can also work with the points. Now to work with points, you can make use of Cartesian coordinates or polar coordinates, any of these, whichever you feel comfortable or whichever is your required as per your work. Make use of that and create 2 points. Now 2 points are here. I don't know if it is visible to you, but let me try to zoom it. Okay, so here 2 points are there. First point is here and the second point is here and the line body is here. So now to this body, we will assign some cross section. So go to your prepare tab where you have dedicated section for beam where you can extract that we have already seen. Now we are going to assign a cross section, and here you have standard library existing based on your uh, work. You can choose from that or you can create your own. So let's say we are working by 50 by 50 cross section, so we'll assume to have a rectangle cross section here. And now you see here beam profile, right? So just expand this one. Whatever profiles you are keep on adding here, those will be visible to you. And just say rectangle and edit mode. Now, when you say edit, no, you will have some default cross sections assigned. So that you need to change it. Go to ruler dimension and here you are able to see 10 mm, right? So make it to 50. Okay, so the breadth is defined. Now you define the height for this one as 50. So now we have got 50 by 50 as your cross section. Can make use of your use control minus to zoom out and plus control plus and control minus for zoom in and zoom out operation, or else you will have to go here and do your zoom in and zoom out. Okay, so since your geometry, I mean like cross section is ready, now you can get back to your structure where you can define your beam cross section to your line and your point. So for line body, just take your cursor there and leave it. Okay, so this cross section creation, you can do it. Create, select your line, and then go to display and say solid body. So your solid body will be visible here, right? So, or you can also work with your points as I told. Select the point, and here you select the point and go to complete solid mode. So your beams are ready. Now for our analysis, we don't need two beams. We are only comparing it with one. So I'll just delete one. Any of the procedure you create your beam, you can use it. Now the benefit of working with points is like when you are playing with your coordinates, right? So you can have a quad for whenever you're working with the point, you can only place your point in 2D, right? So XY direction you will have to place it. But if you have to get it along in the Z direction, I'll show you the procedure. But let us first finish this one. Okay, so let me just save this one as 1D geometry and get back to your workbench. Let me know if you want me to show your beam creation once again so that I'll show it once again to you and then proceed further. It's almost same everything whatever we are following. So I want you to do the simulation for 1D1, and wherever you are getting stuck, let me know. To import geometry, I'll go to browse and import. So 1D geometry I'll import from here and get back to model. Okay, so this is your line body, and now to display your cross section, you can keep your cross section on, and for surface bodies when you are dealing you can keep these thick shells and beams on so that you are able to see your cross section. Okay, so let's just go with default mesh. You can also directly solve your problem, no issues with that, and go with static and then once again say fix. Now I'll just keep this off and go with vertex selection. So vertex is selected, and next, insert and say force. So in the opposite direction, here I'll apply a force in the downward direction, right? So I'll change this to components. This is for people who have not done, and apply a loading condition and click to solve. Okay, so this is the procedure. Now, when you look at this complete procedure, no, you can see here, first thing is the mesh one, which you have already known that when we are dealing with 1D body, we have 43 nodes and 21 elements. Okay, and when we are dealing with 2D one, when I look at my mesh, I have statistics of elements. I have just 72 elements, and that's what when I'm dealing with a 3D geometry, I'm having like almost 84 elements here and 651 nodes. So we know that whenever we are solving a problem, at every node there are six equations being solved, right? Three translation and three rotation. So as your number of elements get increased, you will have a long more solution time takes longer here, right? since this is a simple problem, you're not able to make difference like what when you're solving a 2D, 3D or 1D one, but when you're dealing with some complex problem. So at that time, definitely converting your geometry to 2D or 1D will make an good idea for you to work. And this is basically the simplification when you work on it. And along with that, you also have to work on assigning the proper boundary conditions and get your results. Now when I look at my results in case of 3D, I got it like deformation of 0.31. Okay, and when I see my results for 2D one, I got my results here also like 0.31. And also when I'm solving for 1D one, I got close to that like 0.32. So like where I have here as 0.3 19, I have it here 0.32. So like almost like whenever you can work on converting your solution since you're not getting much differences. So it is only applicable when you have to apply when you're applying the proper boundary conditions and good mesh you are adding it. So these things will work you out. And also with this procedure, whenever like whatever throughout the sessions, whatever journey you're going to have with learning with the simulation, you can incorporate wherever it is necessary, either working with 3D, 2D or 1D. So that was the main agenda, to show you in the same geometry and same boundary conditions and getting different like how we are going to use it for different problems. Okay, I hope till here we are clear. To be play like I want to play with the coordinates, so I'm not using actual dimensions now, but yes, I'll show you the procedure how to play with your coordinates. So as I told you, when you want to play with your coordinates, you have to place points and then you have to place it, right? So that you can make use of polar and Cartesian, and then you can make it, let's say I keep it 50 from here and 50 from here. Okay, and also 50 in this direction. Okay, so this is like I have created for me as I have come up here, and next I'll go back to 3D. When I go back to 3D, I can select one of the point and take a plane creation there. So when I do like this, I'm not able to do it. So that's why when you are at the back, when you're creating itself, you take a plane here. So now you can see your plane, right? So this plane come back to 3D mode. Now when you have a plane, you are able to see that Z coordinate is activated for you. So when you're placing plane points, that time itself take plane and make use of move tool, select your plane and move it at certain height. Let's say this is also somewhere around 40 mm. And now if I have to place points here, I'll place my points and the plane in such a way that my background points are visible for me. Or else if I place it like this, then I won't be able to see my points. So I have to place it in this direction and say to sketch mode. So now my points are visible. And if I want to place my points at same direction, directly I'll place it there. Or you can same way polar or Cartesian coordinates, you make use of that and try to create it. So now we have created the points, and same procedure, go to your prepare, take some cross section, once again edit it, whatever is your cross section you take that, edit, let's say 10 by 10 itself, I'll not change it. And to create, I'll select my line, like where I need to connect this connectivity. Right, and whenever you want to break the chain, just say escape and once again say create. So you can have different cross section for different connectivities. So mostly this application works out when you're working with some chassis creation and all, no? So where you have to work on the beams and all, so you can make use of this one, or some trusses and all. When you're creating, you can make this procedure used. Okay, so this is how I have created. I mean, like I have placed my points in 3D dimension, and now all these things you can align some proper geometry and I mean like dimensions, and then you will be able to see your proper connectivity. I hope this is clear. This was just in case anyone is working on this kind of problem, they can make use of this technique.
Learned a lot about the geometry, what is how to find out how to do the geometry creation with help of Ansys best claim. Then there comes a behavior of your body. So whenever you will be selecting any part of your geometry, it will ask you the stiffness behavior. So whether it is a flexible or it is a rigid body. Okay, so now we are dealing with structural analysis. So mostly it will be flexible bodies. Rigid body dynamics is another part of the Ansys mechanical. Okay. Then in your structure, you can have point mass, you can add acceleration, you can add standard earth gravity, you can give rotational velocity to your structure. Coming to the material properties, so whenever you are doing a static structural analysis, few material properties are needed, that is Young's modulus and the Poisson's ratio. Okay. Then density is required whenever inertia loads are present. Like whenever you are doing any of the vibration analysis, density is required. Then thermal expansion coefficient is needed whenever you are doing any of the thermal analysis or you are applying a thermal load, then you need thermal coefficient of thermal expansion. Okay. So going ahead one by one, I will tell you about the material properties, what would be needed. So as of now, you keep it in your mind that for doing a static structural analysis, I need Young's modulus and I need Poisson's ratio. Okay. Then there are various types of contacts we will discuss as we go ahead. So how it plays a role. So whenever there is the combination of the bodies, so there are 5 types of contact that we will discuss one by one. And whatever may be the analysis settings, I will discuss. Okay. So now what once I will be doing is boundary conditions. Okay, so I have one geometry of a two-dimensional rack and gear and rack. So you would have seen gear and rack many times. Okay, right? Whenever you are doing your practicals, or there are many examples, right? Rack and gear. So here I have one rack and one gear. So I will be applying some remote loads to it. So so what I will do, I have just for your reference, Sangeeta has shared some folder with you, right? In that folder, there will be a geometry called 2D rack. Okay, so I'll be writing here. So what it is there, so that you can or you can write it as a 2D gear step. It is there. So I will write it in the chat box. So you can search for this geometry in your shared folder. Can you locate this gear set 2D? Begin our problem. So we are doing a static structural analysis. So I will tell you what is the problem. So I have one gear and one rack assembly. So as of now, for simplification purpose, I'm considering it as a 2D model. Okay, I'm not considering as a 3D purpose because we have seen we can simplify any problem, right? just to save our time and the solution time. Fine. So now what I will do, I will be selecting here static structural. So you can locate here static structural, double click onto that. And then you can, before that import, you can just go and import, and you have to select gear set 2D. Okay, so you can download that image and then you can do that. Fine. So I have here ready with me. So I'm just doing that. Are you done? Okay. Now see, now I'm right clicking onto the geometry and below I can see properties. Okay. So I will just click on the properties, and now here at number 21, you can see analysis type is 3D. But I want to simplify my problem and I want to make it 2D. Okay. So I just click on the arrow beside it. Okay. And I will just change it to 2D. Fine. So now I'm done over here. Now I will open the model cell. Any doubt till this point? My 2D gear set looks like I have one gear, you can see here, and I have one rack over here. Fine. So since I have made it as a 2D one, I will anytime whenever you are working onto any problem, one, you have to keep on checking the units. Units make a lot of difference into your solution. Fine. So I'm checking. I want my units to be in kg. I want it is in a kg, mm Newton in that this manner. So I will select this one. Fine. Now you can click on a geometry. So you can see here. This is your rack and this is your gear. But now check onto the thickness. By default, software has taken it as a 1000 mm. Okay, but I know the thickness of my both gear and my rack is 12 mm. So I will just change it to 12 mm. Fine. Now Now you can see, click on the geometry and here you can see 2D behavior. Now in the beginning itself, I have told the software that I am going to do it as a 2D analysis. So by default, it will ask you what type of behavior is this. If I click on this drop down, I get many options: plane stress, axisymmetric, plane strain, generalized plane strain, and by body. So for this particular problem, I will be
Yep,
selecting.
ma'am.
Yeah,
Mhm.
great. Okay. So now I was here. When I click on a geometry, I can see the 2D behavior, plane stress, plane strain, axis symmetric. Okay. So now anyone knows what is plane stress condition? What is plane strain condition? Can anybody tell me? The difference in the stress, okay, that is 0. Okay, we write right dz particular problem I can solve it by taking it as a 3D, but you have seen the beam example. There is not much change in your solution, right? The whatever the stress or the deformations you are getting out of it, there won't be difference. You are just simplifying your problem. Fine. So this is, I'm considering it as a plane stress condition. That's what I wanted to share over here. Fine. Then now what I will be doing now, here it is a 2 geometry. Till now what you were doing, you were dealing with only one material. Let's have a check on the material. So for both it is a structural steel. Now go to coordinates. So it is a global coordinate system. It has taken by default. So now we will go to connections. Okay. Since there are two bodies, there should be some connection in between them. So it has a contact and this is your contact. Okay. Can you see this? So this is that whenever two bodies in contact with each other, you have to define the contact region in between these two bodies. Okay. Now tell me how the function of this would be, how this gear would be rotating. Can you do you agree with that? Right? And if I apply some force on the bottom of my rack, then this rack will also be moving in the translation direction, right? So now I have to assign the contact between these two bodies. So now you can see the type of contact. Okay, so there are total 5 types of contact. One is bonded. Bonded means two bodies are, please understand this concept very carefully because this will help you whenever you are working with the large assemblies. Okay, so bonded means two bodies are sticked to each other. Okay, just join your two hands. Okay, like a namaste position. So these two hands are sticked to each other, and now these hands, I'm not allowing them to slide over each other and not separating from each other. So they will always be glued to each other. So such type of, whenever such type of physical condition in the contacts is there, so you will be assigning bonded contact to your body. Okay. Now second is no separation. Okay. The name itself says that two bodies are not allowed to separate from each other, but in this particular type of contact, both palms, rub your both palms. So your palms are allowed to slide over each other, but they are not allowed to separate each other. Such kind of contact is called as no separation. Clear? Okay. Now just keep this thing only in mind. Going ahead, I will be telling you about the frictionless, frictional and contact. Okay. Now coming back to our problem, this gear and this rack are allowed to slide over each other, but they are not allowed to separate from each other. So which contact I will be using here? Can anybody unmute and tell? Please be interactive, unmute yourself and tell, because the physics behind this is your bodies are allowed to slide over each other, but they are not allowed to separate from each other. Fine. So now I have assigned no separation contact. So whenever you are importing any body from any software to Workbench, by default, Ansys will assign bonded contact. But you have to understand the physics, and accordingly you have to assign the contacts to your bodies. Okay.
Ma'am, but is this no separation without friction?
Now I will be, yeah, it is no separation without friction. So let us say I will just tell you quickly about other types of contacts as well, so your doubt will be clear. Okay. So now bonded and no separation contacts are called as a linear contacts. Okay, because it is not changing its behavior or it is not changing its status. They are not getting separated, status is not changing. There is another contact called as a frictionless contact. Okay, so the frictionless contact is the one which is similar to no separation, but it is allowed to separate. So there are few conditions where your contacts are allowed to separate, your bodies are allowed, there is a possibility that they will get separated out from each other, but it will be sliding over each other. So that kind of contact is called as frictionless. And there is contact called as a frictional, where the bodies were sliding over each other. It will have some coefficient of friction between them, and these bodies are allowed to separate also from each other. So this kind of contact is called as a frictional. There is one more contact, is a rough contact. Okay, So rough contact is whenever your uh, coefficient of friction is very high. You would have seen the conditions where coefficient of friction is very high. So that time we use rough contact. In this particular, the behavior of that contact is the bodies are allowed to separate from each other, but they are not allowed to slide since your coefficient of friction is very high. Okay, so the frictionless, rough and frictional, these three contacts are called as a non-linear contacts since they are changing their behavior, they are changing their status. That's why it is called as a non-linear contact, and bonded and no separation are your linear contacts. Fine. Okay, done. Now I am done with, I have given some, we are done with the contacts. We have given thickness to our both of the bodies. Now let us go ahead and do the another things. That is, we have to now give the uh, boundary conditions, like we have to apply load, we have to apply supports, right? So now what I will do, I have this inner edge. Okay, so this is, so I will be taking some point. I need some point on to the center of my gear because it is not there to apply the loads. Okay, so what I will do, I will select the edge over here. Just go to edge selection, right click and insert remote point. Okay, you got it. So what I did, I selected model cell, then I just did a line selection, right click, I inserted remote point over here. Okay, so remote, what is the remote point? See, this problem is very conceptual. You may find that I'm telling lots of information, but this will be help you in going ahead. Okay, so what is remote point? First, understand the concept of remote point. Fine. Now you all are sitting on a chair, right? Now, if I will tell you, I'll ask you, what is the CG of your body? So it will take you or any software to locate the CG or the center point of your body on that particular sitting position, right? The remote point is a point where it will choose the boundaries of that particular surface and it will consider one point away from your body, and that point you will be applying a load so that the load will be equally distributed over the boundary which you have selected. Okay, so that particular point which I have selected from away from my boundary is called as a remote point. So in the many places, whenever you get confused, like where to apply a load, whether I should apply load on a node, or I should apply it on an edge, or I should apply it on a surface. If you are confused, if you know that the application of load is throughout the surface, but you don't know where to apply the load, you just select that boundary and consider a remote point and you apply loads on the remote point. Okay,
Ma'am,
is that clear? Yeah,
hello. Yeah, ma'am. Okay,
that time
fine.
only you have to assign the contacts and then you will be doing the meshing. Fine.
Okay, got it.
Fine. Now coming back to a problem. So everyone clear about the remote point? Otherwise, I will be showing you one picture that will make your doubt clear. No doubts means everyone has understood or nobody has. Can you imagine the remote point now? Okay, please repeat. Fine. So now remote point is what? So let us take example of this pipe. Okay. Now, if I want to apply the force on this particular pipe, Okay, this is a hollow point. I don't know where to apply the force. I can just click on this surface, or I don't know what to do. And we are being encountering with such particular conditions, right? So what I will do, I will select the boundaries of this particular uh, pipe, and I will consider one point which is away from that boundary, and I will apply a force on that point, that is on the remote point. So that remote force will be equally distributed over the area, or the whatever arbitrary location you have taken equally. Okay, so you will be apply the load. Maybe sometimes you can apply the boundary conditions on the remote point. So whatever it may be, you can apply it remotely. Can you imagine it now? From this particular picture, it would be more clear, isn't it? Any doubts further? So a remote point can be defined as an arbitrary location, and then it is scoped to the existing geometry as desired. So a specific remote condition may then be applied on the remote point. Okay. Yeah, someone wants to ask and something problem now, since I have considered this 3D geometry as a 2D one. That's why I'm considering the remote load application over here. Okay. So now I will be applying the loads and the boundary conditions over here. Fine. So now what I will be doing here, now what I will do, I will go to structural analysis. I will insert a remote displacement. Okay, so now here you can see different forces are there. So whenever you are doing a structural analysis, first of all, it will be giving you, can you understand this? So this R first 4 are to be applied onto the body, that is a 3D body. Fine. Then pressure, hydrostatic pressure force can be applied on the surface. Okay. Then coming to the fixed supports, those are also can be applied on the surfaces. Fine. So now what I will be doing, I will be giving the remote displacement. So I will go insert and I will click on the remote displacement. Okay. So now it will be coming as remote displacement. So geometry, so here is a geometry selection. So here is a drop down. Okay. So now I will be giving it to a remote point because I will be applying a remote displacement over here. So you have to give here a remote point, that is a remote point. You can rename it if you are feeling confused over here. Now for the remote displacement, since I am working on a 2D geometry, I am working on a 2D problem. So it will ask me X component, Y component. That is a translation along X and Y direction and rotation in the Z direction. So what I will be doing, I will be freezing out all the remote displacement. I will be doing it 0, 0, 0. So my displacement, it is not allowed to display in X, Y translation and even into the Z rotation. Okay. Just remember these all boundary conditions. Okay. Now at this edge of my rack, I will insert a frictionless support. So you have to provide supports as well as you have to provide the loads over here. Fine. And here at this edge, I will be adding a force. Okay, force into the upward direction. So what I will be 2500 Newton of the force I will be applying into the upward direction. So I will take the component and it is 2500 Newtons of force. Okay. So can you see this? What I have applied? Remote displacement, frictionless support and the force. Fine. So now I have got what are the things I would be interested to know. I would be interested to find out in total deformation. So I will be finding the total deformation. Then let us say I will just solve this. So just right click and solve. Okay, so can you see the total deformation? So total deformation, I have got it 0.01588. Okay, so I can just animate it. Can you see what constraint I had given over here? My rack, this gear was not allowed to rotate or translate. Only my rack is moving in the upward direction. Okay, can you see this? Can you solve? Can you solve? Okay, so now I have seen it is a plane stress. Then what I will be doing, I'm giving the thickness to my both parts is 12 mm. Okay, please note down these things. So thickness is 12 mm. Then I will go to the connections, its contacts, and I have assigned no separation contact. Fine. Now remote point, I will just remove it. Okay. Press. So what I have to do, I will go to model, okay, then select a line selection, right click, insert remote point. Okay, fine. So it's done. Remote point. Then I will connection, no separation. Now I will go to analysis setting. I will ask the remote displacement. So here instead of geometry selection, I will be choosing a remote point. So now it becomes remote point 2 for me over here, but for you it would be only 1. So now remote displacement I am giving 0, 0, 0. Then I am applying frictionless support to the edge of my rack, and I am applying 2500 Newton of upward force in the downward side of my rack. I inserted total deformation and just solve. Fine. So I have got my deformation completed. And mode shapes, you must be drawing some matrix, right? Eigenvalues, eigenvectors. Are you doing these things?
Yes, ma'am.
Yes. So this is what now we are going to do this onto your software. Okay, you are doing this, whatever you were solving, that is the analytical approach. Now what would be the simulation approach in doing the model analysis? Now first tell me why we do model analysis. Every component which is being generated or you are working on to any of the product design and development life cycle. So natural frequency plays an very important role. Yeah, someone has right resonance condition. That is the important reason, right? So resonance should not happen. Resonance is some the phenomena where the whole your structure can be destroyed. Okay, so to avoid that, we are doing natural frequency analysis. Okay, so if someone is working on a product design and development life cycle, the important part is to find out the what are the stresses are being generated onto your structure. So we did a static structural analysis. We found out the red ones are like those are the failure prone zones. Okay, so you can make go back and modifications into your designs, and you can make it more safe, right? You have various things to be considered whenever you are working onto any geometry or any of the product which is to be developed. Okay, so the engineer should think in all aspects of that. You can check on your fatigue criteria. You can see what is the life of your component you are getting. If you are getting the less life, then you can go back and make changes into your design. So finding out the natural frequencies is one of the basic criteria. Okay, even before going to apply the forces, the the simulation engineer has to check onto the natural frequencies of your structure. Okay, why I asked you the natural frequency of a human heart. So I just wanted to know if you can tell what destruction or can happen. So people get heart attack. Why it is that? It is, you can consider it one of the resonant phenomena, right? So such kind of things to not happen, what we are doing is we are doing the modal analysis. We are finding out the natural frequencies of the systems, so that my component's natural frequency on its own free vibration frequency should not match with the forced frequency, and the resonant phenomena should not happen. Okay, so everyone must be the people we have starting learning about the vibration. The first famous thing you would have learned into your book as well, the famous Trachoma bridge that just collapsed within the 6 months of the construction. Okay, so that is the very famous example. From that point people started learning about the free vibration concept, natural frequency concept, because that collapsed just in 6 months, and that is due to the resonance happened onto that structure. Okay, so for that reason we are doing modal analysis to find the natural frequency of the structure. So there are various things to be checked by a simulation engineer to do the modal analysis, that I will discuss one by one, and you have to do that. Okay, now the equation which is running at the back end of the software is nothing but your this equation of motion. Okay, so you know the equation of motion, mx double dot plus cx dot plus kx is equal to 0 for free vibration, and mx double dot plus kx c dot x plus cx dot plus kx is equal to f for a forced vibration. Okay, so now after calculating this is your final equation, k minus omega square m into pi vector is equal to 0. This is the equation which is running at a back end of the software whenever you are doing a modal analysis. Okay, so this is the equation. So k is the stiffness we discussed earlier as well. Then damping is not present. We are not considering damping over here. We are considering undamped modal analysis as of now. Okay, going ahead, you can explore those things as well. You can see on the damped modal analysis as well. Fine. Force is not present since it is a free vibration analysis, right? Now, whenever you are doing a forced vibration, so what is being done over? Someone has raised a hand, Gajendra. May I know if
Yes, ma'am.
you would have calculated eigenvalues and eigenvectors? Okay. So for this particular modal analysis theory, so K and M are constant. Okay, your stiffness matrix and mass matrix will be constant. So now think come like how I will get mass matrix. Okay, which of the material property will give you the mass factor? Fine. So whenever you are doing any of your modal analysis, So you should have Young's modulus, Poisson's ratio, and density as a material property to be inserted into your material properties. Okay. Why density? Because density will give you. Anybody can tell me why density is required?
Ma'am, we need mass basically, and mass can be given by a formula of density and volume.
Exactly. So density is nothing but your mass upon volume. So whenever you are drawing any geometry, volume will be calculated at the back end of the software by just taking those dimensions of your body, and mass plays an so mass will be calculated from it since you have put density as a input to your body. Okay. So now I uh, problem, right? Bonded, no separation, then a rough, frictionless. So now whenever you are doing any of the dynamic analysis, whether it is a modal analysis or it is a harmonic analysis, random vibration analysis, transient analysis, any of the dynamic analysis you are doing, all your contacts will be considered as linear contacts. Okay, they won't be considered as linear, non-linear, what I said in the structural analysis. So whenever you are doing dynamic analysis, all your contacts will be considered as linear ones. So rough will be treated as bonded, frictionless will be treated as no separation, and frictional will be treated as a bonded contact. Okay. So now let's do a problem so that your concepts will become over here. Linear perturbation procedure is different, my friend.
Ma'am, this theory.
Selecting modal analysis. Okay. So please open your workbench. So now I will be drawing a simple geometry. I will take a plate. I guess you guys are now very well versed in Ansys space claim. So just start Ansys space claim and draw any plate of your choice, any direction. You can make hole into your plate, anything. Okay. You don't need to follow me. You can even take different geometry. Do not care. Okay. I will take a simple plate of my choice. So don't tell me to go back to geometry and do the changes. Okay. I have taken a simple plate. That's it. I drawn a square, I draw a rectangle, and I took this, just extruded it. I given some thickness to it. That's it. Nothing rocket science. Okay, so now this is my plate. Now just follow me. Okay, just see what is happening. Okay, don't do anything. Okay, you can do this later on. So this is one plate. Now what I have done, I'm just I open Ansys mechanical over here. I'm not doing anything over here. Just in the analysis settings, I will go to analysis setting, and I will just maximum modes. I will make it as 10. Fine. That's it. Nothing else I'm doing over here. Just right click and solve. So this is called as a free run. Okay. I have not applied any boundary condition. I have not applied any force. I did nothing. I just did a free run. So now, can you see this tabular data? You can see the first 6 frequencies are 0. Can you see this is 10 raised to minus 3 and this is 10 raised to minus 2, means it's 0. Do you agree? So why these first six frequencies are 0? Okay, I will tell you the reason behind that. So now every body, it have its own inertia. Now I'm working into the three-dimensional space. So it has total 6 degrees of freedom, 3 translational and 3 rotational. Okay. So total 6 degrees of freedom are there for a body. And whenever you are extracting mode shapes, those are first 6 mode shapes are called as a rigid body mode shapes. Okay. Since you have not applied any constraint, that is you have not applied any boundary condition, that is you have not fixed anywhere, or you have not given a remote displacement to any of the edge, you have made everything is free. So that's why you are getting first 6 mode shapes, that those are the rigid mode shapes, as 0. 7 onwards, you started getting some frequency. So your first frequency, natural frequency is 2885.6 hertz. So that is the inertia effect. Okay. So first 6 are the rigid body mode shapes, and 7th onwards you are getting some the mode shapes. Those are called as a flexible body mode shapes. Okay. So whenever you will do a free run, you are going to get it like that only. Fine. So why we need to do free run? Okay. Now let us say I am working onto some assembly. Hmm? There are some 8-10 parts which are connected to each other through contacts or joint or anything. Fine. So now whenever I am working on an assembly, first run I should do is a free run. Why? Because I will get to know if any of the part is not connected to each other. Okay. If any of the part which is not, so I will get to know. So ideally I should get in a free run first 6 natural frequencies are 0. But if any part is not connected to each other, it will start showing me the frequency. So free run is every time necessary whenever you are doing any of the assembly natural frequency, if you are finding the assembly's natural frequency. Fine. Now what I will do, now I will give remote displacement. I will show you. I will apply the remote displacement at this edge. Now what I will do, I will make something 0. I will make Z component as 0. And make 2 free. I'm making any 2 free. Okay. Now can you guess how many frequencies I will get? 0. Anyone can guess? Anyone who thinks first four frequencies will be as 0, since you have made 2 of your boundary conditions as free and rest, or you are making it as a 0, that you are constraining those. Okay. So this is about the free vibration analysis or a modal vibration analysis. You can make it. And now how to extract the mode shapes out of it. Now what I will do, I will just suppress this and I will apply the another one. Insert. I will apply fixed support. I just apply fixed support. I will solve it. Okay. Fine. Now what I can do. So now how to extract mode shape results. So right, you select all right click, create mode shape results. And now you can see the deformation, total deformation of your all mode shapes. So you can see this is your first mode shape, this is second, this is third. You can see the animations as well. Fine. So can you do this now? Two things. One is a so I will not show free run now, okay? You have to just right click and run. You can in analysis settings, you can extract up to n mode shapes, okay? No issues. You can make it 10, 12, 20 as per you need the mode shapes, fine. Now what I will do, I will just right click and insert a remote displacement on this edge. I will make something now 0. Direction 0. Solve. Select all, right click, create mode shape results. Again, I will go to right click, evaluate all the results. And now I can see the total deformation of every mode shape. Okay. Okay, who is showing Sweetie? Very good, Sweetie.
Moving towards the next part where we'll be able to do the model analysis with the pre-stress condition. Okay, so if you have seen in yesterday's session, so you have used this model analysis system over here. So in the model analysis system, we generally solve for the various mode shapes when we don't have any pre-stress condition. But in the case where we want to add a pre-stress condition, we need to connect the static structural with the model analysis. So for that, first you need to add the static structural, and then you need to add the model analysis to the static structure. So you need to drop it in this way so that it will share the engineering data, geometry, model, that is meshing, and then it will transfer the result to this setup of the model analysis. So you can see it is transferring this engineering data or it is sharing the engineering data, geometry, model, and then it is transferring the solution from the static structural as an input to the model analysis. So we need to create a connection this way. Okay, so once we done, then we need to go for the engineering data where we can add the different engineering data as per the requirement. So now let's say we have the default material that is structural steel, and if I want to add any new material, so let us say this is go to this engineering data sources over here, and from this engineering data sources we can add a new material. So simply just select the general materials from this, and here we have the list of the various general materials available. So let's say I wanted to add material, let's say copper alloy. So just select the copper alloy, click on plus sign, and the material will be added. So this bookmark indicates that material is added into the library. You can see the properties of copper alloy over here in this, sorry, it's not yet selected. When you select this copper alloy, you will be able to see its properties over here in this property row. And but here you cannot edit any of the property of this particular material. So if you want to edit the property, then again you need to go back to this engineering data sources. So and it will show you only the material which we have added into the project. Okay, so here you can see the copper alloy, and if required, you can change the material properties over here. So like this, you can add any new material into the current project. Okay, So once we have added the material, now simply close this, and now we need to create a model. So simply go to this geometry where we are going to create a model. So just double click on geometry, and here you can see it is showing starting specific. So here we can create the model.
Uh, uh, yeah, can I sir?
Yes, yes,
Yeah, we
please.
can. Yeah, we can move a little slow so that the participant will grasp each and every step.
Oh, okay.
We cover.
Fine, sir. Yeah. Okay, so now we are into the space claim, and let's say we wanted to create a simple plate with a hole. So let's say I wanted to create a rectangular plate. So for that we need to take a rectangle over here, and let's say we want to create it from the center. So here we have option define rectangle from the center. Okay, simply enable this option, and then you can start the uh, this rectangle from the center itself, and then you can give the dimensioning. So let's say it is of let's say 100 by 200 mm, or let's say 250 mm, sorry, 100. Okay, so this plate has been created, or let's make it as 200 only. Okay, so we have created this rectangle over here, and now to create a hole, so again take a circle command over here, and now I again want it at the center. So create a circle, let's say we'll create it of 25 mm diameter. Okay, so like this we can create the rectangle. So process is very simple. When you enter into the space claim, first take the rectangle command, and then you have to select this option like define rectangle from the center, and then select origin as a center, and then create a rectangle of 100 by 200 mm. Okay, once this is done, then select the circle, then again start the origin of the circle from the this coordinate system. So just start from here, and you can give the 25 as a diameter. Okay, so like this we have created the sketch. Once we finish with the sketch, and now we need to return to 3D to convert it into a surface body. So here we have option return to 3D mode, or you can just go for this end sketch mode. Okay, end sketch editing. Okay, so just say okay to this, and it will be return to 3D. So here you can see on the left side, now it is completely the surface body. If I'll undo it, and if you see again over here, now it is a line. These are the different sketch bodies. Okay, but when you return to 3D, it will be converted into a surface body. So like this we can create a surface out of it, and once this is done, then we have to go for the uh, okay, we need to remove this circular face. So just select it and just simply delete it, so it will be removed. So that will be as a hollow a plate with a hole. So we have this complete plate with the hole. So let's say we are going to solve it in 2D, and with certain thickness to the sheet metal, right? So that thickness can be directly added into the mechanical side. So no need to give the thickness here. We can have it as a 2D model. If you want it in 3D, then you can give the thickness. But if you just need to have it as a 2D problem, then you don't need to give the thickness over here. Then you can just define the thickness in the meshing, or in the mechanical tab. Okay, so now we have completed with the model, and once this is done, then close the space claim, and then go for the workbench. Okay, so here as you can see in the workbench, now it is showing geometries having a green tick. That means geometry is updated over here. And the next step is to create the model. So just go to the model, double click on it, and it will start the mechanical. Here you can see starting mechanical. Okay, so let it get open. Okay, So now we are into the mechanical. And just switch to the geometry mode, and here you can see this model is imported. Now one thing if you observe that in the geometry we have this question mark over here. So whenever we are creating a model in mechanical, and if it is a sheet metal or a 2D model, we need to define a thickness to that, because whatever the calculations will be there, their thickness will also be considered. So you need to select it, and here you can see we have in the geometry we need to select the surface model, and in the surface model you can see in the details of that surface model we will be having the option thickness. So just click on this thickness, and let's say now this thickness is 0, so let's say I want it of 2 mm thickness. Okay, and now once I give the thickness over here, you can see now it is having the green tick over here. Okay, so like this you can easily add the thickness to the model over here. Okay, once this is done, now we need to create a mesh for this model. So simply select the next step, that is mesh, and here you can see the physical preference is already given as mechanical. Let us create a default mesh first. Okay, so just right click on mesh and click on generate mesh over. Okay, now you can see it is a very coarser mesh, and having a 17 no, element size, maximum element size. So we can change it. Okay, so before that, if you want to change the units, okay, so you can just go to the home page, and here we have option units, because using the same unit what we have used in the modeling is very important over here. Okay, so by mistake, and you should not give some other values, that need to be kept in mind. Okay, so let's say we'll try with 5 mm, then right click on mesh and again generate the mesh. Okay, but still you can see mesh is better, but still it can be more better. So let us make it as like 2.5. Here you can track the meshing progress. Okay. Okay, still we can just go for, let's say, 1.5. Generate the mesh. Okay, I think I directly solved it. Okay, okay, no issue. So you can see mesh is updated over here. It is good mesh, but not 100% good quality. You can see it's of a mixed type of mesh. It has stat elements as well as the hex element over here. Okay, so you can see now we need to update, or if you want a complete hex element, then you can add a method like hex dominant. So let us say we'll add a method to, okay, quadrilateral dominant. Okay, not hex because it's a 2D model, so it's we can try with the chord mesh over here in the complete body. Okay, but still it has not created a complete hex dominant mesh or quad dominant. You can see there are some um, triangular elements are also available over here. Okay, so that also we need to understand. But if you still want to improve this, you can just, go further. What you need to do is you need to split this particular surface into different parts, and then you can go for a structure mesh over there. Okay, so we'll just have this kind of mesh as of now, and okay, so we'll add the stress condition. Now once the mesh is done, okay, it's automatic. Okay, we try with all quads with multi-zone mesh. Yes, can anyone tell me what are the different mesh quality checks that we need to understand? No, discretization or dividing a continuous body into a finite number of small elements. That is nothing but a meshing. So why we need meshing? So we can, solve the various finite element or flow equations on each control volume. Whatever the each element is nothing but it is called as a each control volume. So if we are talking about different, then we have different methods over there. So then why again we can solve the geometry, we can have a good representation so that we can apply the boundary condition at specific locations. That is the reason we need a mesh. So what are the different significant impact of mesh on the various things, like we have the rate of convergence. So exactly what happens, so let's say we have a one bar of 10 by 10 by 100 and we are dividing it into let's say 100 elements. Okay, so let's say now I want to solve the equations for each node point. So whatever the number of nodes generated for that 100 elements, and whatever the time it will take. Let's say it is taking 5 minutes to solve that particular problem. And then let's say what I did is next time I have again discretize it further to 200 elements. Then ultimately what is going to happen? Software has to solve these equations for more number of nodes again. So definitely your time will be increasing. So with this what happened, your solution time or CPU time requirement, that will be increased. But with this what will happen, when you're solving the equations 100 times for the large elements, and when you're solving it for 200 times for the small elements, so you will be able to capture that result variation when you have more number of nodes. So with increasing in number of elements, your solution accuracy will be increased, but your CPU time requirement will be more. Means it will take more time to solve that particular problem. Again, whatever the convergence criteria we set, if we are having more number of elements, the convergence will be taking more time to get converged. Solution will be taking more time to get converged. So these are the different impacts of a mesh on these different factors. So that also we need to understand. So let's say you are creating 1,000 element or 5,000 elements or 1 lakh elements or 1 million elements. So depending on the problem, depending on the requirement of solution accuracy, sometimes you are not much interested into getting only the results. You are just interested in finding out the area where we are getting that bad quality or weaker part, or maximum deformation region, etc. So we are, if interested into that and not much into the accuracy of the solution, then you can have little coarser mesh also. That will help us to get a faster solution in a lesser time. Okay, so that is how we can solve this problem or complete it faster. Okay. So here you can see um, we have two different methods over here where problem can be solved. In finite element or for FEA, we solve with the finite difference method, where results will be solved at each node point, and whereas in finite volume method, the problem or results will be solved at each control volume, and the results will be stored at the cell center. So these are the called as cell centers over here. Okay, so like in 2D we have this types of element like triangular, quadrilateral. In 3D we have tetrahedron, hexahedron, pyramid, wedge, prism, then polyhedron, polyhex, for different types of elements available. Now, the nomenclature, which is very important. So here you can see in case of 2D, now whatever the plate problem we are solving, that is a 2D problem. So this point joining the element is called as node point. The side of that particular element is called as cell. This is complete cell or element, and this is a cell center over there. Whereas in 3D we have this node point. This is the complete edge. This is the face, and this is a complete cell over there. Okay. So I hope you understood this. Now, okay, we'll move back to the our problem. So depending on the you know the type of model we have, we need to choose what kind of mesh we have to create over there. So for this kind of problem, if it is in 2D, we can definitely go for a very good structured mesh. But just for a time being, I am solving it with the unstructured mesh over. Okay, so let us see. Now I have created this complete model over here, or I have created the complete mesh with 1.5 mm elements. So let's say I'll make it a final of 1 mm elements, and then we'll move to the next part. Okay, I try to create all hex elements, but still it is not creating in a proper way. So you can see they are just giving randomly placed elements. Okay, and with some bad quality cells as well. So to understand that, you can just check out the display style. You can change it to, let's say, element quality, where you can understand. So there are some elements where we have the element quality of 0.25, that is 25%, so which is a bad one, right? So if you want, you can improve the element quality in those regions. So let's see here we have the element quality, which is a bad one. Okay, so you can improve that particular quality elements as well. Okay, so once we're done with the mesh, then now we need to go for the static structural, where we need to give the pre-stress conditions to the model. Okay, so let's say we have this plate fixed on these two edges. Okay, so let us add the static structural, go to the insert and add the fixed support. So let's say we are adding fixed support on this edge and this edge. So go for the edge selection with this, select this edge, use control and select the other edges, click on apply. So both the edges are selected only. Okay, so there we have applied the fixed support. Now again, right click on static structural, insert, and let's say we are going to apply the force conditions. So let's say we'll have some force on this circular profile or the whole side. Okay, so click on apply. So let's say we are adding a downward force. So in the downward direction, we have negative y-axis over here. So change this from vector to the components, and here we can give minus 9.81. Sorry, not gravity, we are adding some let's say 1000 Newton force, so it should be minus 1 kilonewton force that we have added over it, as you can see this location. When you click on this static structure, here you can see at A and B we have the loading conditions or the boundary conditions. So at B we have fixed support, and at A we have the force of 1000 Newton. Okay, right. Then once you applied the required condition, now we have given some pre-stress condition to this plate. Okay, and now just simply right click on static structural and solve. Okay, here you can track the progress. Okay, so problem is solved. If you want to see the stresses occurring, so you can go to the solution, right click, insert deformation total. Then you can add another, let's say you want to add stress values. So right click on solution again and evaluate all the results. So here you can see these are the stresses which are generating into this. So I'll just remove the one. So you can see stress generating over here. So this is the deformation and this is the stress value, these locations. Okay, so as you can see, we are getting a maximum stress of 726 MPa. Okay, over here, and then we are getting the total deformation of 3.4717 mm. Okay, now this is not actual true scale, it is inline scale. If you want to see the true scale, you can just see over here. So this is how, this much is the difference that we are getting in an actual case. Okay, if you expand it, you will be able to see that with this you can just scale up the result so that you can
Yeah,
see the proper variation. Yes, any question?
so there is a question in the chat box. There is
Okay,
a query in the chat box.
uh type of the solvers. um In what way? We have the FEA solvers, we have various CFD solvers. Basically, here we solve with a finite difference method or a finite volume method. Okay, so in CFD, we have explicit implicit solvers. In FE also we have explicit implicit solvers. So depending on problem to problem, we need to select the various analysis systems. No questions? And so please try out the problem and try this. Any doubt?
For the built-up model, otherwise.
No, I think they can create it, and that will
Yeah,
help them
sure.
practice as well. Just a moment, sir.
Or if you have the built-up model, otherwise.
No, I think they can create it, and that will
Yeah,
help them practice as well. Yes, so we have this model. So if you want, I will just take a drawing sheet. Yes, so we have this model that will help them practice as well. Yes, so we have this model. So if you want, there is a hole at the center of 25 mm diameter. Okay. So, and in the meshing, you need to give a thickness of 2 mm to this sheet. Okay. Structure do is you need to take this static structure. Yes, so what you need to do is you need to take this. शो करो किसी ने like how much you have completed in the screen. It can help you when I lag. Okay, next I'm still loading. You have done. So we have come back to otherwise. Swapnil show to show communication. Touch it not yet yourself, so I think you can share your screen. Need to. Sir, actually the total deformation you have added is in a wrong way. You need to click on solution. Hello, am I audible? Yes, click on solution and then you will be getting a graph in the center. You can see. No, don't right click. Just see in the center of the screen. There is a graphs. These are different graphs which are coming. Just expand that. You can expand that by pulling it in upward direction. Yes. So right click on that. In the graphs, right click. Click on select all. Again, right click on the graphs. Create mode shape results. First option. Yes, so that is how we need to add it. Now right click on solution and evaluate all the results. Yes. And you can see different mode shapes and the results related to each mode shape will be there. Okay. 1 mm, so which is too much actually. Layout. How much thickness is mode shapes and the results related to each mode shape will be there. Okay. How much thickness is given for the plate? Go to the home, reset layout. So it is 10 mm, so which is too much actually. Okay, so that is the reason we are able to see the plate of that larger size. So you can have 2 mm or 3 mm. That's like what I have done was that is for 2 mm. Okay, yeah. Then you can again resolve it. Yes, so this way we need to try the problem. Oh, like how sir, or who has some Vikesh to show. Okay, Abhi who want to show, they can just raise their one by one. Those who want to show, they can just raise their hand. So I will call one by one. Okay, so you have added 4 total deformation results. Why that so? That is the wrong one actually. Okay, so just delete all of them. Delete all total deformation results. They are not required. Right click on it and delete. Yes. Yes, so that's what I said. If you want to show me, I won't understand what problem you are facing and I won't be able to correct it. We whatever the in model analysis, whatever the results we add, that we don't need to add it by right clicking on solution. This thing keep in mind. Okay, what we need to do is we need to click on that graphs in the bottom side. Okay, then right click on it. Just right click on the graphs. Result. On static. Solid. Solve. Share the screen and show me if you have just fine. So okay, so we'll see the next problem of parametric study. So what is okay, so we'll see the next problem of parametric study. So what is parametric study? So see the okay, so we'll see the next problem of parametric study. So what is parametric study? So this study is performed to understand what is the effect of on the results by changing certain parameters. Okay, so let's say if you talk about this particular problem, so let's say here we have this particular sheet. Okay, what if I initially I have given the thickness of this sheet as 2 mm. Let's say I want to try out.
Excuse me. Yeah,
Yes.
are you sharing the screen? I cannot because we
Oh,
cannot
okay.
see it.
Sorry. Just a moment. Yeah. So let's say in this particular problem, so let's say initially I solved this problem for 2 mm thickness. So let's say instead of 2 mm, I want to check out for the let's say 1.5 mm, 2.5 mm, like how much weight is increasing and whether what are the results we are getting, whether those are changing or what. So that is what how the results are varying, that we need to understand, and that is completely depending on the uh, modes, that is called as a parametric study. So by changing a certain parameter, what is the effect on the results I will be getting, that we need to understand over it. So many times what happens, so we go for certain over designs. So what I mean by over designs, like um, uh, let's say you are designing a chair and it should sustain let's say 50 kg of load, and but you are designing in a such a way that though you are keeping a 100 or 100 kg of load, it is still sustaining that. So what exactly it means is our requirement is of only 50 kg, or it should sustain a weight up to 50 kg. So let's say with the safer side we are designing for 60 or 70 kgs, but if we are designing it for 100 kg of load, and what exactly it is happening over there is you are going for a over designed cases. So that is something not required. That will unnecessarily add more material, and that will make a model as a I know weight to the model. So that thing we don't need, right? So that for that purpose, parametric study is very important for you. So for that, let us say I will create a model. Mm, Let me share the new screen. Just a moment. Okay. And let's say we are going for a simple static structural analysis. So we'll go with the uh, this same engineering data. We'll just add the okay. So just launch this specifically. Okay, and let us say we'll create a model over here. So we'll create a rectangular profile on this XY plane. Okay. Let's say it is 50, 100 by 5 mm. Okay, and return to 3D. And I'll create a path. Okay, on this plane. Let us say it is 150 by 150. Okay, return to 3D. Okay, sorry, not return to 3D. We need to give some rounded corners. So let's make it as 50 mm. Then return to 3D. So what I have done is I have created a profile and a path. So let's say I want to pull this particular profile along this particular path. Okay, so it is created. Okay. So once the model is created, now you can see I will add a rib over here. Okay, so which will connect both the sides together. Okay, or it will give certain support over there. So let us go to the design, create a design on this particular plane. Okay, and let us create it of let's say it should start from the it is 150, right? So it should start from 100. So take a cursor to this location, press shift and give the this as -50, and it should go till here. How much it should be? Okay, what we'll do is we'll project this project to sketch. Okay, this edge, and this edge. Okay, so from the midpoint of this edge, we'll draw till the midpoint of this edge. Okay. This midpoint is nothing but a 50 mm only, correct? So trim excess part here and here. Now if you want to measure it, press E to measure this, and here you can see it is of 50 mm, or this one is also 50 mm. So you can see from this point till this point it is 50 mm. Okay, so it is correct one from this point to this point. It is 50 mm. Okay, so done. Return to 3D. Okay. Indexes. It has created unnecessary edges over here, so just remove that. So now it is a closed loop. Yes. Okay, and now we need to pull it on both the sides. So let's say we'll pull it on both sides, and let us give a thickness of 5 mm. Okay, done. And now we'll add two holes on this faces. So let us say in the middle, press shift, and let's say it is at 25 mm. Okay, sorry, press shift, should be -25, and here let us create a hole of 10 mm diameter. Okay, it is too small, let us make it as at 20, and it is of how much is possible, 20 mm will make it. Okay, so similarly we need to create it on the other face as well. Just remove it, so hole is created. Similarly, we need to create another hole over here on this face. Again, take a cursor over here, press shift to take the reference. It is 20 mm, and here it is 20 mm. So return to 3D and press H for home view and remove the material. Okay, so we have created this bracket over here. Now what we need to do is go for the selection, select this face and use control and select another face over here. Okay. Okay, so what we can do is use ruler over here. Okay, so take a pull command, select this face and use ruler up to this face. Okay, and okay, cancel. Once we add this ruler, click on this P. So this parameter set will be added into this group. So you can see this ruler dimension. So it is added over here. Now let's say instead of 5 we want it as of 7. So you can see it will be added over there. Okay. So we have added this, thickness as a parameter over here. Now, with this changing in thickness, how the stresses will be changing, that we need to understand over it. Okay. So when you have created these two models, so okay, it is single model. So changing in the thickness of the model. Okay, so with changing in this thickness, so we need to understand how the stresses generating in the model will be changed. Okay, so what we are going to do is we are going to fix this face, okay, over here, and this face as well. So like it is fastened on the some surface, and there is some load applied on this part. Like let's say there is some other component which is attached on this side. So it will be having certain loading on the, or else it will give certain stress onto this bracket, and we need to understand how the that's deformation in the bracket or the complete stress in the bracket will be changing when we are changing the thickness over there. Okay, so just a moment, I'll just uh, okay, so yes, understood this. Actually we don't need to add a mm, thickness over here, so we have to create it as a surface body. So what I'll do is I'll just undo this. Let it be. I will convert it as what.
Yes, screen is not visible.
Okay, so you can just go to prepare and go for the mid surface.
Yeah, your screen is not visible, Mr. Kailash.
Sorry, yeah, sorry. Okay. What we need to do is, so we have this model. So go to the prepare, and here we can take a mid surfaces of the models. Mid surface is not possible. Okay, so you can see surface body I have created. Actually, you don't no need to worry. You can simply create a this kind of shape over there. No need to worry. Okay, so I'll just once we created this particular surfaces, now we need to give the connections. Like you can see, this is one surface and this is another surface created. Okay, so now what we need to do is we need to add a um, connections between them. So you need to share this and share at this location. So it will add a share topology over there. So they will share the connections. Okay, so you can see this surface one, or I'll name this as a rib. So right click on it and rename it. This is a rib, and this will be the bracket. Okay, so we have named it. So just no need to give the thickness. Apart from that, everything is same what we have done. Okay, so I hope you understood the model, or shall I repeat it again? Yeah, anyone want me to repeat this?
Yes, sir. Please repeat.
Okay, I'll just delete it completely and I'll freshly create it. Okay, so simply what we need to do is now I'll create directly for 2D. So just forget about 3D. So no need. Okay, so simply create a line. So let's say I'm creating a line from the center and it is of 100 mm. That line is created. Now return to 3D. So we have this line. Okay, take another plane which is perpendicular to this. So let's say we are taking this XZ plane. Okay, and now here we need to create a line. So let's say it is of 100 and then it is of again, sorry, actually it was not 100, it was of 150 mm. Okay, and now here we need to create a line. So let's say it is of 100 and then it is of again, sorry, actually it was not 100, it was of 150 mm. So 150 in horizontal and again 150 in the vertical direction. Done. Right click and finish the line. Now give the rounded corners. Exactly click on the point and it is of 50 mm. So here you can see return to 3D. So we have this line and this path. Okay. So create a sweep command. So select this line, take a sweep command and then select this as a path. Use control to select all three lines. Okay. Done. Say pull full. Clear till this?
Yes, sir.
Clear, right? So surface is created. Now we need to create the rib. So again go to the sketch mode and create a sketch on this mid plane. Okay. Now in this what we need to do is take a projection of the existing sketch. So project this, this and this. Now take a line from the midpoint of this to the midpoint of this. Okay. Now trim the excess part. So this one and this one need to be trimmed. Okay. Return to 3D. So we got the rib. Clear? So this is the bracket. We can rename this, right click on it and rename bracket and then done. Clear? Understood? Yes or no?
Hello, sir.
Yes.
Sir, what about holes?
Yeah, holes will create it. So this one is clear till here. So just then we need to share the topology. Before that, you can create a hole. So holes. You can go to the design sketch mode and select this plane. Okay. Take a circle and take it from the center. Press shift button to take the reference. So let's say we need to take a reference at 20 mm. Okay. 20 mm. Press shift. Here we have the reference. Okay. 20. And then from there it is of 20. Done. Return to 3D. Select this surface. Click on delete. It will remove the material. Okay. Similarly, create a sketch on this face. Take a cursor to this center line, press shift and give the distance as 20 mm and give this diameter as 20. Return to 3D, select this face and delete it. Holes are created. Okay. Now what we need to do over here is we need to give the share topology so that they will transfer the load in between. Okay, otherwise they both will act as a separate component. So go to the workbench and click on share and enable the share along all three edges. Okay, sharing is done. Okay, shared three edges done. And that is how we need to create a model. So any doubt again in this model? No, then bench and launch the model. Okay, so now you can see it is added over here. Now, when you see this rib and bracket, both are available. So let's say we have this rib, thickness is given over here. So let's say currently we will be adding a thickness of let's say 2 mm. Here you can see before this thickness there is a box. Click on that box. Okay. And when you are clicking on that box, you can here, if you come back to the workbench here, you'll be able to see parameter set is added over there. Similarly, if like a parameter set is added, so just double click on it and it will show you the parameter set. So you can see this rib thickness. This is your parameter set. This is input parameter that you need to change. That's what it is showing in this way, this arrow. This is input. What output you want to observe with respect to this input, that also we need to set. Okay. Again, go back to this. Now select the sorry, bracket. And now for bracket, let's say we are giving the thickness of 3 mm initially. Again, click on parameters. Okay, so this P, it will add it into a parameter set. Again, if I double click on this here, you can see two parameter sets are added. One is a bracket thickness, second one is a rib thickness. Okay, in the output, what we need, let's say I wanted to observe the mass of this particular model. Okay, so here we can go to the properties and here we can see the mass. Click on this, it will show you the mass of the rib, or sorry, if I want a combined mass, so you can just simply click on this SYS and in the properties. Okay, here we cannot add. Let me see here. Here you can see this is a combined mass. So total mass of rib plus bracket that we want to observe. What will be the total mass? So click on mass. So let's say I don't want my rib or this complete bracket and rib mass should not exceed like 2 kg or 3 kg. I have some restriction. So you can just check out the mass. So when I go back to the workbench, now here you can see this is the output set added. Okay. Here you can see these are the inputs, and with respect to that there will be output. This is output. Here I cannot add this value, that will be calculated from this inputs. Okay, now we have added them too. Okay, now let us create the mesh. So I'll give a 2 mm element size and generate the mesh. Okay, so mesh has been created. So if you want, you can even still improve the mesh. Let's say I will give 1 mm. Generate the mesh. Okay, so you can see the better mesh has been created over here, and there is a contacts also. Okay, so actually we have already shared, so it will not show this contact over here. Okay, so once we done with this, now here you can see we need to go for the static structure. So let's say we are fixing this plate from this face. Okay, so just select this face, right click, insert, fixed support. Okay, and let's say on this side or on this edge, there is a force which is acting, let's say, in the upward direction. So, or upward or in the outward direction. So we'll add it in negative Z direction. So force. So let us say we have a component, let's say minus 10,000 Newton. Okay. So I have added the force. Okay. So here you can just click on static structure. You can see these are the parameters. If you want to vary the force also, you can see this in the force we have this Z component. Let's click on this P. That will also be added into the parameter set. This is the input. So you can see it is editable. I can edit this. This is the output that cannot be editable. That will be the result of what we are solving. Okay, or what we are giving the input parameter. Depending on that, it will be changing. Okay. Again, we need to give a fixed support at this location also. Insert are not required. Actually, we have to fix the plate on the bottom side. Okay. Now we need to check out the results. So go to the solution, right click, insert, let's say deformation, and go to the solution, right click, insert the stress. Okay. So when you go to the stress, so what stress value you want to observe? Let's say I want to find out the average or the maximum, what is the maximum deformation that I want to find it out, and what is the maximum stress. So select the stress here. Also we have results maximum. Click on this box. So this P is added here. Also P is added. If you go back here, you can see these two values are added over here. Okay, like this. These two values are added. Now, once done with this, so let us solve this problem first. If it is not required to solve, okay, it is up to you if you want. Let us not solve here. So here you can see we have given all the inputs and what output we need, that we have given all, right? So let us say I want to change these combinations and find out the result. So right click on this DP0. Here we have option duplicate design points. Okay, now you can see new design point is created. Okay, now add one more. Let's say I want to add four combinations. So again, go for duplicate design points, and duplicate design. So total 5 are created. Okay, 0 was the first one. Let us say now I want a thickness of 2.5, and this thickness, this plate thickness also 2.5. Here, okay, it is should be 2.5, and here I want it as 3, and here 2, and here 2.5, sorry, 2.5 and 3 and 2 and 2.5. So these are the various combinations I have given. Understood? Now, with respect to these combinations, what will be the mass of the complete component? What will be the maximum deformation and stress generated in the component? That we need to understand. Now, if I wanted to solve each case one by one, it will be taking long time, right? So instead of that, we can just create this kind of design points in the parametric study, and then here we have option update all design points. Just click on it, and it is asking you to close this some editors, like this editor and this one is will be closed. So say yes, and it will be automatically closed. Here you can just click on this show progress, and it will show you the complete progress over here. Okay, and here you can see now it will start solving. So first we'll get the maximum deformation over and the stress value over here. Okay, and you can see it will be updating. So you can see for design point 0 now it is solving. Even I have just changed the thicknesses. I have not changed the this force input. Then this can also be changed over here. Okay, so it is completely up to you how you want to change or what parameters you want to vary, and to you want to observe the results. So you can see for design point 0 results we have received. Now it is solving for design point 1. So you can see weight is already calculated. Now it is calculating the like stress and deformation. You can see for second also it is done. Now we can go for the third one. Okay, for third also weight is calculated. Now calculating the stress and deformation. Okay, so you can see 3 design endpoints are already solved. Now it is solving for the remaining 2 cases. Okay, and you can see solution is completed. Now it is just retaining certain data, and once that will be done, we can see the results. So you can see already we have got the results. So for the first case, you can see we are getting a deformation of 14 mm. Actually, it's reopening the whatever the closed editors were there. So you can see 14 mm and 8081 MPa, that was the stress generated. For the second case, you can see the mass is 0.62 and stress or deformation is 21 and the stress is 10,007 750. In the third case, you can see it is again more since we have inversed the dimensions over here. In the fourth case, you can see it was 2.5 and it was 3. Okay, now in this case you can see we are getting very less stress with this combination and very less deformation as well. So you can check. So let's say you can consider this is the best design point, or this could be the best combination for your particular problem. So that is how you can analyze this. So let's say you want this, so you can just set this as current. Let's say you want to observe the results for this particular case. So right click on it, set as current. Okay, so yes. Okay, once set it as current, then you can go back to the project and you can just double click on the model. It will show the results for that particular case which we have set for the current. Okay, and here you can see this deformation, how it is getting deformed. Okay, they have stresses are generating over here. So those things can be observed over here. You can see this is the maximum stress is 7527.6 MPa and the maximum deformation is 13 mm. So that is for this particular case. So that is how you can get the results for the different combinations, and then with this you can understand which case is best suitable for your problem or for your application, and accordingly you can use that. I hope you understood this. Any kind of like anything you want me to ask? Yes. Any doubt? Any query in this complete problem? Is there any query? Please. First create a profile. So in this case, profile is simple line. So I have selected XY plane, select a define a line from the center and create a line of 100 mm. Line is created, correct? Now return to 3D. So we have this line. So line is along XY. So we need to create a profile either on XZ or YZ. Okay. So once we created this, okay, so we need to create another profile either on YZ or XZ. Okay, so in this case I want it in a vertical direction, so I should create it on YZ plane. So take a line command again and it should be on the YZ plane. So select it this way, like this. Select this plane, so YZ is selected. Okay, and okay, so we need to take it along in the vertical direction first. That will go in the horizontal way. Okay, so take this, let's say 150, and then again in the 90 degrees angle 150. Okay, escape and then go for the rounded corner. Okay, so here you take the rounded corner and here give the radius of 15. Return to 3D. That's all. So once you return to 3D, now we need to select this line as a profile and take this sweep command and select all these 3 lines as a path. Use control to select three lines and just simply I think it has had some issue. Just a moment. Okay, so select this line, take a pull command. Okay, I think it's you need to take a pull command, select this line, then take this sweep option, then select line 1, 2, and 3, and you need to click on pull full. I don't know, it's not at all responding. Just this way we need to create it. So I just dragged it. Actually, this pull full option is not getting highlighted. Okay, so this way we need to create a profile, right? Now to create this rib, it should be exactly on the middle plane. Again, middle plane is YZ. So again, go to the sketch mode, take a YZ plane. You can simply click on X axis to create a YZ plane. Okay, say look at. Okay, I don't know, that's also not working for me. Okay, so once we created this plane, now here again take a line command. Sorry, no need to take line command. First take projections of the existing features. So go to the design. Okay, go to the sketch. And then you need to use this, you know, this project to sketch option over here. I don't know, for me it's not working. Okay, try till here. I'll just restart this. So space claim, it's not at all responding. Okay, so I'll simply create it again. It's 150 and then 150. Return to 3D. Okay, done. Take a sweep command, select this, select the line, take a sweep command, select 3 lines, 1, 2, 3, say pull full, done. Then go to the design, take a sketch mode on this middle plane. Okay, and here what you need to do is project to sketch. So project this sketch, and this one. Okay, so all will be projected. Okay, actually it is creating twice, so I'll delete one. Okay, one more time I'll try. This one, and this. Oh, okay. Not the construction line. Okay, so I have created all three. Now take a line command from the midpoint of this till the midpoint of this, and then trim the excess part, this one and this one. Okay, return to 3D. Done. That is how you can do it. To create a holes, again go to the design, take a sketch on this plane, and here create a sketch of like a circle. Take a circle profile, take a cursor to the midpoint, press shift, drag it downward 20 mm, and there create a circle of 20. Return to 3D and just simply again create a sketch on this plane as well. Take a cursor here, press shift, give the dimension 20, again 20, and then return to 3D. Press H, just simply delete, select this and click on delete, so it will be removed. That's all. Clear? Clear with this?
Yes, sir.
Yeah, please try it. So see, modeling can be any way. So we have this particular problem over here. So we have this complete pump housing over here. So this pump housing, which is kept at or which is exposed to different temperatures at different locations. So you can see this inner surface. So this surface is exposed to interior which of the pump where the fluid is contained, and it is at 90 degrees Celsius. Another thing is this mating surface. It is held at a temperature of 60 degrees Celsius, and this outer surface which is exposed to a temperature of 20 degrees Celsius or which is exposed to air at 20 degrees Celsius. Okay, so these are the three conditions for here. So go back to the workbench. Now we need, I do have this model ready with me. Okay, so just need to go to engineering data. So let's say we want to compare for the two cases. So one is a metal and another one is a plastic. So I'll go to engineering data. I need to add both the materials, right? So let's say I'll add aluminum alloy and polyethylene. Okay, so add both the materials, click on plus, and here you can see both the materials are added over here. Simply close this engineering data. Now geometry we already have, so I'll just right click on geometry and import the geometry, and then just select the geometry, pump housing dot stp. So double click on it. Just a moment. Okay, so here you can see this model is here. Now we need we can see the model here. Now we have to apply the various conditions. So we can say this is the housing. Now let us create the mesh. So I'll just directly give a mesh size of 3 mm and generate the mesh. So everything is same. Instead of applying the static structural boundary conditions, here we can apply the thermal boundary condition. Okay, and in this case, if you go to engineering data, here you will be able to see only thermal boundaries, that is thermal conductivity and material field variables. You can see along with that change in the temperature. Okay, you can see the complete data over here. Okay, so these two values only that we are getting here. Okay, so you can see all the materials as well as their properties here itself. But in this case of mechanic or thermal analysis, only the thermal properties which are important over here. Okay, so in which you can see this isotropic thermal conductivity and specific heat concentration. Okay, so these are the thermal properties which are important over here. Now we have this model with us. Now we need to apply the boundary condition. So right click on steady state thermal, insert, and you can see only thermal related boundaries now. The first one is the temperature. So we need to apply temperature on this surface, all the inner surfaces. What you need to do is select any one surface, and here we have option extend to limits. Automatically the selection will be extended. I'll hide this mesh so you can see it very carefully. Okay, so it is selected. Click on apply, and on this surface temperature is 90 degrees Celsius. Now you can see the unit is 90 degrees Celsius. If you want to change it, you can go to the home units, and here you can see if it is in degrees or Celsius or Kelvin, you can change it. Okay. Now this surface which is exposed or which is connected to other part of the pump housing, which is at 60 degrees Celsius. So select this face, right click on steady state thermal, insert temperature to this face which is at 60 degrees Celsius, correct? And then now this outer surface which is exposed to air at 20 degrees Celsius. What it means by exposed to air at 20 degrees Celsius? There will be convection from the surface of the this pump housing to the air. Okay, so we need to add a convection boundary condition. So go to steady state thermal, insert convection, and where we want on all the outer surfaces. So select any one surface again, click on extend to limits. You can see all the outer surfaces will be selected. Click on apply. Now film coefficient, if you have value you can directly add it, or I want to import it from the tabular data. So here you can see import temperature dependent, and I'm going to take a simplified stagnant air simplified case. Okay, so you can, it's just a value that we are getting. So if you don't know, you can directly, if you have direct value, you can directly put that value, doesn't matter. And this air is at 20 degrees Celsius. So add that, and that's all. We have added all the boundary conditions over here. Simply right click on steady state thermal and solve the problem. So very simple it is, and you can easily solve. Okay, once done, now right click on solution, insert thermal temperature. Again right click solution, insert total heat flux. Okay, again right click on solution and evaluate all the results. And here you can see the temperature variation. If I remove the grid, so you can see the complete temperature variation. Since it is a metal body, so you can see complete heat transfer is taking place from the inner surface to the outer surface. Okay, so you can see temperature is varying from 60 to 96 Celsius. Okay, okay, now you can see the heat flux. You can check out the direction or vectors of the heat flux over here. Okay, now important is how you can see this temperature variation. Now actually we have solved it for the static structural. We supposed to change the material. So I'll just go to this pump housing again. Material assignment, change it to uh, aluminum alloy. Okay, and then again I'll solve it. Okay, you can see the temperature variations again. So this is for the metal. So I wanted to again have the same results for the plastic also. So what I'll go do is again come back to the workbench, click on this arrow and just duplicate this. Okay, and here you can see its copy will be created. You can name this anything, like this is for the plastic and this is for the alloy. So you can name that as well. Okay, so just again double click on setup. Okay, So you can see here, just need to go to this geometry again. Select this pump housing, change the material from aluminum alloy to polyethylene and solve the problem. That's all. Because everything is same, we just need to find out the result for the other, or we can say the plastic material. Okay, we can go for parametric study, but there we can only see either maximum, minimum, or average temperature, but we cannot see the complete temperature distribution. So in that case, we have just duplicated, and here you can see this is due to plastic material or having a less thermal conductivity. Here you can see there is no heat transfer taking place from inner surface, or it is very less, as you can see. Okay, so that is how we can make a comparison out of this. Clear with this? Any doubt in this complete portion?
No, sir.
Okay. So, sir, how I can share this geometry with the participants? Is there any way? Okay, you can upload it here.
Okay, please put it in the chat. I'll try to look into it. And whenever let's like we have discussed like working with some linear contacts, then in the similar way when you're working with non-linear contacts, there is a issue that comes out like when you're defining the contacts, your contact status will be open. So basically whenever you're defining contacts, it should be closed as in the status, so that your load transfer is going to take place properly. So now when you say in case of having a friction value, if all the time you can have some gaps and all, but when you have gap, how to overcome those issues? So that is, you can make use of your pinball region. So let's say between the two surfaces you have 2 mm difference existing or 5 mm difference existing. So specify a pinball region that's saying 5 mm or 10 mm of pinball region, which will help them in terms of and you are giving an software input that yes, because of between these two surfaces, or you can say between these two components, there is some load transfer taking place, right? So in that case basically you can use this pinball radius. So I'll let you know, or maybe in the further today's session you will get an understanding like what are the different formulations are there, detection methods are there, and how exactly you can work with this. All right. So when we talk about connections, um, uh, like I hope till yesterday you would have only seen about the connections, right, in contacts. But other than that, you also have certain joints existing. So now the question comes where these kinds of joint comes up. So basically, I'll give you an intro like even this helps you out in terms of just imagine you're working on some rigid body motion. Okay, so where you have to define your load using your joints, right? So reference you give there as a joint, so definitely we should have an idea of working with the uh, like joints. Then even in static condition, wherever you have this sliding nature, other than that, if you have to specify some input, or like you have to give some moment or something, so in that case you can also make use of this revolute or the different types of joints existing. So now I have an example for every type of joint when and where this you can make use. So like you have first one is the revolute one. So in this condition you can allow to have a rotation along one axis, that is z axis you can have. Then next one you have is the cylindrical joint where you see rotation along one axis and also translation along one axis. Then next you have is the translation joint. So basically when you talk about translation, the translation is only allowed in x-axis. So in that condition you can specify the coordinate x where it should have a translation. Okay, so that you can specify. Next, there are slot joints, universal joints, and also spherical joints. So these are basic. Now, since I'm giving you an example to look after it, you will be able to understand that yes, whenever these are my conditions, I can make use of this following joints. But anytime you are getting stuck up, you can just make use of ANSYS help. I'll show you how to even get these things, get an idea. Even these pictures and the videos that I've taken are from ANSYS help, because that is the source from where we learn and also you can learn. Okay, then you have spherical joint. Next, you can also have some planar joint and also a bushing joint. So these type of joints, I hope you just let me know if you have seen how to add some joint in your geometry. If someone could answer, it would be really nice. Okay, Abhinandan says by mistakenly has raised. Okay, so you have not seen how to add a joint. Okay, so let me show you. Just let's take one simple geometry which you have already seen during the meshing one when I was trying to show you. I'll just open the same folder. Okay, so till here, any question you have, you can let me know. And yes, for your joints also, I'll show you few examples when we are trying to. So now, once I show you now how to define this joints, it's very simple. You would have already seen yesterday. But yes, this defining joints and working with joints, it's important a bit. So I'll just enlighten a few things. And in future, anywhere you're working with those things, just you can let us know. Any one of us, you have given to connect with so many people who are already working in this field, so as you can say that it's an add-on advantage for you. Okay, so now basically you see when I just say delete this one, whatever is the existing one. Okay, so basically, whenever you are importing a geometry, that is assembly, I can say, by default, some connections will be generated for you. So in case you delete them anytime, you can get it by saying connections, insert and connection group. So when you take a connection, you can say create automated connections. Automatic connections are being created, right? So when you create your automatic connections based on some tolerance value, so like we have here connection, and when I'm trying to decide create all this, let's say I'll delete and show you. Tolerance is one of the important things when you are dealing, like you will be ending up having lot of components coming up. Like this is just a component of hardly 10, 10 are there in this, and but you will have more than 400, 500 thousands also you can have the components. So in that case, to detect those connections, it's important to play with the tolerance value. So you will have certain categorization that yes, wherever this 5 tolerance is existing between the surfaces, I have to detect only those bodies. So you can group them, you can keep them together for your reference whenever you are changing. Because when you work for a geometry once, that is not your end result. You need to keep working on that, right? So let's say I have a tolerance slider here. Auto detection method is there where you can define. So when you say 0, so default tolerance value like 0.73 mm it is considering for detection. But if you say you want to have something like or you can define 0.5. Okay, so directly when you want to give a value, change the slider to value, and tolerance value you define to 0.5. And now you say to create automated connections. Okay, so when I expand this based on my tolerance that I have provided, all these contacts are been detected. Okay, so now one more advantage you can say that when you play with the tolerance value is you can have multiple tolerance values. But if you say only if you have an understanding that yes, these two components are capable of going with zero point 0.5, then you don't have to manually select, but instead yes, within that range you are by default creating it, and you don't have to go to every contact and you don't have to check yes this is a workable or no. Just check if you have a tolerance value with you, then you can play with that and select all these. And you can also say rename based on definition, so whatever is the naming given to each component, based on that also you can get it. And so um, the best thing is you work with lot of things. Okay, you have your boundary conditions ready, you have your mesh ready, and you are ready to solve. But somewhere you are getting stuck with your connections and you don't know how to deal with that, then definitely you are not going to get the result. So that's more important to have an idea about contacts working. So that is why especially this a portion of time is dedicated in order to deal with contacts. Few things even for static, when you consider, when you consider for a non-linear condition, few more things will comes up. Okay, so now when you say bonded, by default bonded is there here. You can change that to no separation or friction, whatever contact you want to add, right? Then next you can also see there is a pinball region. As I told you, wherever there is a open status existing or some frictional contact, you like non-linear contact anywhere you are using, you can define either auto detection value or some radius value you can give. So when you say radius value, I said like zero point 0.5, within that range, whatever is my detection, they should come up. So I can give around 7 or 5 as a pinball region. So whereas I'll be able to create a pinball here, and this is going to act as a source for the load transfer for me. Okay, so I hope till here it is clear. Now I'll show you how, and you must have already seen how to create manual contacts and also. Am I audible? Let me know if I'm audible. I think in
Yeah,
between I got lost.
yeah, it is.
Yeah,
Yes,
thank you.
you are.
So, yeah, I didn't cover anything in meanwhile. I just got to know I'm lost. So, yeah, so this was just playing with some pinball radius when you have and defining the connections. So, out of that, when you have to define the joint, so I might not have a proper geometry here, but yes, to make you have a proper understanding, like how to define the joint and what kind of joints you have already seen. So, let me just consider three components I'll take to show you how to create a connection, I mean like joints. So let's consider these uh, con- show all first, and I'll suppress all these from here. And when I go to connections, I need to take a connection group for any sort of connection you are defining. Let it be joint, let it be connection or contact. So when I say connection group, now connection type by default contacts will be there. In case you want to change this to joint, change this to joint. And I told you, you can define the tolerance value or slider value you can give and just say to create automatic connections. So when you say this, for these two components, there are joints are created. Now you can same way, if you want to rename based on the definition, definitely you can go for it so that you have an understanding of which component or what kind of joints you have given. So now when we deal with joints, basically kinematic pairs, whenever we talk of saying like either it should be body to body contact that we have auto detection has created for these two, and the other one that you have is body to ground. Okay, so when we are giving some grounded connections, it will create this body to ground, right? So you need to change connection type if you are creating your automated like if you are creating automated one. So by default body to body will be generated, and in case you have additional body to ground connection to be defined, you have to uh, just take a manual creation of joint. So let's say I have joints and say insert and joint. So in this condition you can uh, just go and change from body to body to ground. So when you say body to ground, only one mobile scoping is required for you. Let's say I want to keep select this surface and say to have a grounded connection. So as I told you, this might not be a appropriate condition, but yes, to show you, we have to consider the simple geometries to make you understanding. And for your application point of view, the joints how when and where you can define, you have already seen in the slides, right? So those are few which you can consider. And now you need to define what kind of joints you want to have. So let's say this is a body to body connection, and we have all these different types of joints coming up. Okay, so you can give fixed, revolute, cylindrical, translation. So as I told you, that all these joints, when you're considering, it's up to you. Direct, you can play with any axis, but in case of translation defining, you need to make sure your x-axis is along where you want to see the translation. So now you can see for this component, uh, you can just try to switch. So let me just go with expanding and go with the reference coordinate, and principal axis right now it is considering in the z, because when you select a surface, only in that particular direction it will consider. So change this to x. So now you have changed it to x. So now you can also like check in your connections like how exactly that is going to work using your configure one. So yeah. So when I have the highlighted portion, that will let me know how much it is capable of moving, right? So in this way, you can say we have the configure you can check with your joints. So now next thing what we need to discuss is like a few applications which I can let you know related to. Let me know if you have seen what are the different types of loading and boundary conditions uh, you have to work with. So we can have a discussion on that as well. Yeah, anyone from the uh, like audience can let me know if you want to have an idea about different loads and boundary conditions, and then I'll take you to a workshop which you will have to do and show. So before that, whatever we have seen related to joints and uh, connection, I want you to create some joint and share me your screen. After that we'll discuss the further things, because until and unless you practice anything you won't get. So we can take 5 minutes of spare time to work on this. This one I have showed, so you must be comfortable with this. Okay, so when we say we want to create some automated joint, just go to connections and say insert, adding a connection group. So with this, you can create contacts or you can create joints, that is automatically with the detection method it does. So now we will switch the connection type to joint, and next would be to define the creation of automatic joints. So now we are not defining anything, but yes, we are creating automatic connections, and rest all components what are there, I have suppressed them. Okay, so now in case of these are my body to body joints created. Now anything I want to change from here, let it be revolute, uh, or I want to change this from revolute to translation. So I'll change it from here, right? And then next thing that you can do is create your own connection. So go to joints, insert, and joint. When you say joint, you can change the scoping method, or you can say like connection type to body to ground, and select one of the surface which you want to give a grounded connection. Okay, so this is to create grounded connection. Now type, it is going to be fixed or any of these based on physics understanding you have to keep it, but here for body to ground generally we keep it as fixed. Then next comes up to insert the joints between two components when we are creating manually. So we'll go with joints, and now you see connection type body to body, type is fixed, and then you change it anytime as I told you. Then now reference we have to provide, and also mobile we have to provide. So you can get a view here. Let's say I'll select this surface and define first surface. Now I need to select the internal surface of this cylinder, right? So but uh, selecting separately, I have to hide, unhide, and all this extra comes up. So I'll just select one of the surface, and when the view is available for me, I will modify that. So now you can see we have defined the joint manually for even body to ground and also body to body. So these two things you can do. And for you to practice more on joints, I'll give one workshop for your reference, which after session you can just define this one or two joints, and you can also get an extra knowledge about more working with any of the simulation you are doing now. So it will be nice for you. So this is to open to create any kind of joint. So yes, start doing. And meanwhile, I'll have some example. I'll show it to you when once you're done. So this is for everyone who are not able to do. So first, go to joint, insert, and click on joint. So when you click on joint, you need to provide the two surfaces where this joint should be fit, right? So basically, let's consider this component and this shaft and this pulley I'm going to consider here. So I'll select this surface and click on apply in the reference. Okay, and then where is this surface next touching to? This component, right? Or this component. So any of these two components I have to select and click on apply. Like I have selected just one surface, and then I'll select the internal surface and go down in the mobile section and click on apply. Okay, Krishka, now I believe you can do and show it. Anyone else from the group? I believe girls are not paying attention during session. Three, 4 days, I didn't find even a single girl responding. What you are doing? Share your screen and show us what you are doing. Okay, so let me just give you an example. Like now we have seen the how to define the joints, but there should be certain applications, no, where you are trying to use the simulation as well. So I have this one simple example, no, where I can show you how exactly joints will work for you. So this is one of the run simulation, and you see there are certain joints defined like this. Between these two components there is a cylindrical joint defined. Then you have revolute here for this particular component, and that to body to grounded connection. And then next you have translation here for this nut, right? So and based on these three joints there is a loading applied. So transient condition, yes, you are going to understand in the next workshop, but before that let me show like how you can use your joints to define. So now when I say go to transient, insert, and some joint load I want to add. So what type of joint load I want to add, I can go and say joint load. Now, when I'm trying to apply some loading condition, I can pick out which joint should be used here. So based on if I say there is some translation taking place or what is the rotation taking place. So based on that, like I can define, and degree of freedom you can define along which axis rotation should take place. For you now this is Z, so define this as Z and define the value here. So all this loading condition, as I told you, you'll understand in the further stage. But yes, like I just wanted to show it to you. Even when you are working with your joints, what we have discussed, for your further studies, any transient condition or any rigid body dynamics condition, if you're working, so in that case you will be able to make use of this joints. Okay, and that's how like you will be able to study the behavior also, right? So till here I hope it is clear to you, and let me show you a few more tools which you can use it. So by now you should have used acceleration. I am not sure if it is shown to you, but you can also define acceleration, standard earth gravity, rotational velocity whenever you want to have that you can define. And along with that, you can also define pressure, line pressure, force, moment. So all the highlighted things let you know that what are the possible scoping based on the physics. Then next you have one more, that is hydrostatic pressure. Like if you are interested in studying the hydrostatic pressure, so basically you have to define the fluid density, and then free surface location if you have, you can define or else let it be. So I have a condition which I have solved and kept it, so that I can show you in case of using a hydrostatic pressure. So basically connections are obvious, which which you have seen here. Friction contacts are there. Then you can also see there is a few more tools like compression only support is used. Then hydrostatic pressure is used. So when we use hydrostatic pressure, you have to define where this hydrostatic pressure you want to see. So surfaces you have to define here. Then as I told you, fluid density you can define, and then you can give some boundary condition, that is where is this component fixed. So that definition you are going to give, and some support where it is actually having. So let us see how you can use this compression only support. So before that, I'll just let you know what all more you can explore when you are working. So during the workshop, we would have covered a limited thing, and also you would have practiced limited thing. So, but you having an idea what more you can work, you can at least after 5 years or 10 years or within any time, if you are working, you will have an idea. Yes, we can also work on this one. So bearing loads you can directly define here. Then you can also work on remote force loading, which I think yeah, Sneha ma'am, when she was covering, she would have done a workshop called 2D gear set, right? So with that you would have understood working with the remote boundary condition. You can also work on bolt pretension to work. So directly when you look at the tool here, when you say can static structural or any tool you're using, just go with insert, you have direct to bolt pretension tool to be used. And for understanding what all loadings and all have to be applied, just go to your help. So I would say opening Ansys help is the best thing in case of working. As I told you, like for your joints or something, if you are working, so all that when you work, you need a bit of physics understanding. So where exactly you can get the physics understanding and theoretical things, if wherever you want to see, and how the tool usage should be done. So that you can type there. So let's say bolt pretension, I type, enter. So when you say bolt pretension tool, you can get it here. Mechanical user guide was there, where you can have bolt pretension where you can go for coupled static analysis, coupled field transient or transient. So based on what type of analysis you want to give and what are supported and what are not supported, how all these things works, a detailed understanding is there. Or else a lot of YouTube videos are available, and a lot of information is already available on help which you can make use. Similar way, I told you for your joints you can also see. Let's say I type revolute joint. Okay, so the information about revolute joint is just here. So the whatever examples I have taken for my understanding and also to explain you is mostly from the tool understanding from learn, this you have a help module, right? So from there only I am also taking. So what are more things that you can cover? So you can also work on thermal, which was covered yesterday. So thermal conditions you can work, and you can make use of different supports that are available, like fixed support is there, displacement is there. So whenever you want to constrain in particular axis, so that time displacement you can use. And let's say you want to constrain your z axis, so make it 0, and x and y you can keep it free, or whatever is your condition. Elastic support you can give. Then next you have frictionless support. So basically whenever you have to constrain any of the geometry from a normal direction, it should not have any changes. So in that condition, to constrain a surface from normal direction, you can make use of frictionless support, and this best works out for your symmetry conditions. Then you can also use cylindrical support that we have seen just before, right? Cylindrical support was there. So for cylindrical surfaces, basically to constrain them, or you can say to make it free or fixed in that direction, radial, axial, or tangential, you can make use of cylindrical support. Compression only support you can make use, then simply supported, fixed rotation, and all these you have seen. Now let us understand, we have spoke about contacts today, we have also spoke about supports adding. So first important thing that we need to see is contacts is nothing but between those two between two components you're trying to show how the interaction should take place there, or you can say how the load transfer should take place. But support is something you are giving and condition with an like atmosphere, or you can say in the environment, what should be the interaction that you are going to define. And also as I told you, you would have seen point mass, then few more things in, I think till here anything you have any doubt, like I was going more of giving an idea. In future anything you want to work about around all these things, you can try working, and you can always make use of Ansys help. You don't find anything, just get back to us, we'll try to help you in working with those conditions. Any doubts, please let me know.
So we will start with nonlinear analysis now. What do you mean by nonlinear analysis? How it is being done? So we will be uh, discussing those things now. So So we did static structural analysis before. So what is static structural is, we saw that this is the equation which is running at a backend. F is equal to K into X, where K is a stiffness matrix. So now I had said it earlier during our discussion, that is stiffness is always dependent on your geometry and material. So all the geometrical configurations of the stiffness matrix is being calculated on these factors. So whenever there is any change in the stiffness matrix, that factor defines you whether you are doing a static structural analysis, that is a linear structural analysis, or nonlinear structural analysis. So your linearity and nonlinearity completely depends on your stiffness matrix. So what is this? How if your stiffness is remaining constant throughout your simulation, or your stiffness is changing once you start the simulation. Okay, so So that's how there are three types of nonlinearities: geometric nonlinearity, contact nonlinearity, and material nonlinearity. So your geometric nonlinearity means there is a change in a geometric configuration. So let us take an example so that you will be able to visualize and you will be able to relate it as per your problem statement. So can you imagine a fishing rod? Okay. So initially your fishing rod is straight. Okay. So once the fish is being attached to the end of that fishing rod, what happens to your fishing rod geometry? The geometry abruptly changes. So there is a change in its cross section and the change in the geometric configuration. So such type of nonlinearity is called as a geometric nonlinearity. So whenever we are working on any problem and the geometry changes abruptly as we apply the loads to it. So similar can go with a long cantilever beam and you are applying a good amount of force or load at the end of that free end. So there also you can see there will be a abrupt change in the geometric configuration. So there might be lots of example coming into your day-to-day simulation process where you may have to use this geometric nonlinearity. Okay. Then another type of nonlinearity is a contact nonlinearity, that is called as a changing status nonlinearity. I discussed with you in my previous session that there are 5 types of contacts. Can anybody tell me what are the 5 types of contacts?
Frictional, non-frictional.
Very good. It's a bonded, no separation, frictional, frictionless, and rough contact. So there are 5 types of contacts. Okay. So changing status as in whenever your contact. So we say that bonded and no separation contacts are linear contact. Why? Because their tendency is not to get apart from each other. They are always sticked to each other. Only the no separation contact is the contact where you can have a sliding in between these two contacts. But the behavior of the contact is they are not supposed to get apart from each other. So they are not changing it status. So that's why these bonded and no separation contacts are linear contacts. Please keep this thing in mind that these two contacts are only linear contacts. Okay. Then you have a different another set of contacts which is called as a non-linear contacts like frictionless, frictional, and rough because they have a tendency to get apart from each other. Okay, so that's why it is changing its status. So these 3 contacts are being called as a non-linear contacts. And then comes a very important in my point of view, that is a material non-linearity. So material plays a very important role in the simulation. So whichever material work you are working on, I will first show you the engineering database library which is available in Ansys material library. I hope Sangeeta has not covered that. Engineering data, have you done that? Creating a material library and all? Is it done?
No, ma'am.
Have you
Yes,
generated any material library?
yes, ma'am.
Yeah, you have done with that.
Yes, ma'am.
Okay, fine. So I will not go into that. I will directly show you how to solve any nonlinear problem. Okay. So nonlinearity plays a very important role. So there are different materials available, that is linear materials and nonlinear materials. So when nonlinear comes into picture, so now you have this, everyone is familiar with this graph, right? Stress strain curve for the ductile material. So up to your yield strength or your proportional limit, your stress is directly proportional to strain. Or if you go to this force versus displacement curve, so force is directly proportional to displacement with a constant of proportionality K. Okay. So this is a case of whenever you are solving this static structure or linear static analysis. But if I will try to relate it with the stress strain curve, up to which limit my equation will be linear, till the proportional limit or the yield strength. Okay, till that point your graph is linear. Beyond that your graph becomes non-linearity. So material non-linearity comes into picture after your proportional limit. Okay, so anything in between this happening with your material. So if you go on applying the load, you know what is happening with your material stress strain graph. So your material non-linearity is nothing but the behavior of the material beyond your yield strength. Okay, so so this graph is usually non-linear in nature, and it is different from the graph which you get in the elastic region of your stress strain graph, right? So whenever such conditions will arise, then you will be working on to the non-linear material properties. Okay. So whenever we are working on the nonlinear side of your stress strain graph, the equation of which is running at the back end of the software becomes force is equal to stiffness, which is a function of displacement into the displacement vector. Since you have entered into the nonlinear zone, your stiffness is no longer a constant but constant property. Okay, so it becomes function of the displacement again. So the nonlinearity comes into the picture. Fine. So now if you are working on the linear side, so linear elastic, so for that you need, if you are working on the isotropic materials, you need a basic material properties, that is Young's modulus, Poisson's ratio, and the shear modulus will be calculated on the basis of Young's modulus and Poisson's ratio. Okay, so you know the equation, right? So same equations are there, already been done, calculated into the software. Already that program is there, so that by default it will calculate the shear modulus. Okay, now if you work onto the orthotropic materials, so then you need the Young's modulus in x, y and z direction, and Poisson's ratio for x, y, y, z and x, z plane, and shear modulus will be calculated at a back end. Similarly, if you work on the anisotropic material, then you need 21 models, 21 independent variables you have to define. Okay. Now let us come to the plasticity. I will not go into deep because it will take more than 4 or 5 days to discuss everything in detail. But just I wanted to show what is non-linearity, and you know, right, engineering versus two stress strain curve when the plasticity will be considered. So here, whenever you are working in a non-linear material properties, the most important thing is the yield criteria and the hardening rules. Okay, so there are two hardening rules uh, into their isotropic hardening and the kinematic hardening. Okay, so initial yield surface will always be the yield surface into the elastic zone, and the final yield that is will be this is the plastic region where you will be getting a yield surface after loading. Okay, so your whole material non-linearity depends on these hardening rules. Different hardening rules you have to implement, and you have to specify the material constants as per those uh, uh, hardening rules. Okay, so you know, I consider this is, you know, the principal stress space where you have three principal axes. So this is your elastic zone, and this one is your plastic zone, and this is a uniaxial stress strain graph. So I hope I consider that you know it. Okay, so now understand the difference between isotropic hardening and kinematic hardening. So you understood, right? This is your dotted line is your initial yield surface, and the yellow whole line curve is your final yield surface, that is in a plastic zone. Okay. Now, what is isotropic hardening? So, isotropic hardening is the yield surface expands uniformly in the direction of plastic flow. Okay. So now in the isotropic hardening, there is no transformation of your yield surface or yield surface is being taken at, wherein in isotropic hardening your yield surface expands. Okay, so you can see this black line, black ellipse, you can say black curve is the initial yield surface, wherein this dotted blue line is your subsequent yield surface into the plastic zone. Okay, so in isotropic, just keep in mind, in isotropic hardening, your yield surface expands uniformly. Okay. Now, wherein in the kinematic hardening, what happens? Your yield surface get transferred to another location once the yielding happens. Okay, and it happens in the, it translates into the direction of yielding. So, in whichever direction the yielding is happening, in that direction, your yield surface will translate. It will not change its shape or size. Okay. So mostly whenever you are working on any of the metal, so it's like mostly the metals will be exhibiting the kinematic hardening behavior. Okay. So how to represent this? Now you have seen, see, this is a non-linear curve. Now what the material properties you are giving the software into the material data or as an input is you are giving the linear properties. You are just giving Young's modulus and Poisson's ratio. So but just by considering Young's modulus and Poisson's ratio, what happens? The software will consider, see, software doesn't know whether your material is whether your particular model will be worked on the linear or in a non-linear manner. It will solve as per the initial conditions or as per the settings, as per the commands you give to the software. Okay, so you have to always think about all the things about your model, how it going to behave. Software will give you the result, but the inputs should be correct from your end. The Young's modulus and Poisson's ratio is fine till the point my curve is linear. Now, how you will represent this non-linear part, this curved path of your curve into the software? So there are two ways. One is a bilinear representation and another one is a multilinear representation. Okay. So bilinear means you need to whole of your non-linear, or you just keep into mind the stress strain curve of a mild steel. So the whole curve you have to represent into just two lines. One can be your, you know, the modulus of elasticity, okay, or the Young's modulus, slope of this black line, and another line would be the tangent to your curved path, or it is called as a tangent modulus. I hope you know about the tangent modulus, how to calculate it. Okay, so to represent any of the nonlinear curve, you can to denote it by these two lines, bilinear. In bilinear, you can just note down this. In bilinear representation of nonlinear curve, you need Young's modulus or yield strength and the tangent modulus. Okay. The another way is a multilinear. Okay, means you have to put all the stresses and strains value in a graphical format. You know, right? We do UTM. Everyone has do universal testing machine experiment, right? So you can, from that you can put the values of stresses and strain, and you can plot that complete graph into the material library. Okay. So Bossinger effect. Okay. There are again different types of non-linearity. Okay. Different material models are there. Anand viscoplasticity, Gerson, then Chabochi kinematic hardening model is there. creeps are there. Creep is again one of the non-linear material phenomena. Okay, so this you can the creep also you can represent, you can simulate the creep related problem as well into your Ansys software. Then there is different hyperelastic models like rubber materials are there. So hyperelastic again is one of the non-linear material models. So there are different hyperelastic material models are there depending upon the different depending upon your different taste, because in UTM we have just done the uniaxial test, but whenever you are working on the hyperelastic material, there are different tests. Okay, bilinear, trilinear, shear test data, volumetric test data, different test data are there. As per those, there are different hyperelastic material models are available. You can see here New, Kin, Gent, Munir-Rivlin. Munir-Rivlin is quite famous for tire and all models. So you may have heard about this model. So then polynomial models are there. So these are the different material models related to hyperelasticity. So into material nonlinearity itself, there are different models. Okay, then viscoelastic models are there. So these are the different models available related to just a material nonlinearity. Okay. After contact stiffness, assembly change contact time. How we can consider contact is after contact, the stiffness of attenuation change in contact type. Respect of the also how we can consider bonded contact is a linear contact. See, you whenever you are initially, I am answering to we had used only already available material. We haven't created particular new material. Okay, we will create a particular new material. Okay. I am answering to Alok's question first. Alok, I will show you how to generate a new material model. I will just take some XYZ example. You can include your own material properties. Okay. Now I am answering to Gajendra's answer questions. After contact, the stiffness of assembly change irrespective of contact type. I agree. So how we can consider bonded contact is a linear contact? Yeah, Gajendra, good question. So whenever you are assigning the contacts, that is in the pre-processing stage of your simulation. Okay, you know about your assembly, so you know how it going to function, what your perspective beyond that. Let us say I have some assembly where two parts, let us say two sheet metals should be glued to each other, but after application of load, these two sheets are getting apart from each other. So now whenever you are assigning a contact, you have to assign a contact thinking in a pre-processing aspect, not into the post-processing. What will happen once I apply the load, that you do not have to consider into the pre-processing aspect whenever you are assigning the contact. As per you, these two sheet metals should be glued to each other even after I apply a load to each. Okay, but if I feel like there should be some friction happening in between these two, let us say, surfaces, and they may get apart, then I can definitely go and assign frictional contact. So is as per the initial working of your system, accordingly you have to assign contacts to your model. Okay, means this condition apply. Yes, this condition. So assigning a contacts is a pre-processing aspect. Okay, so you have to assign the contact as per the working of your particular model, as per the physics. You do not have to think about once I apply the load. You don't know whether once you apply the load, it will get apart or it will be still stick to each other. You don't know about that. Okay. So that software will consider. Okay. So it will say that maybe let us say you have assigned bonded contact as you are saying, and let us say after application of load, it becomes, let us say, frictionless. Fine. So that is, so by frictionless as in it is getting apart from each other. So it will definitely show you the solution error into it. Okay. Okay. So now what we will do it, now we will start
Yes,
with,
ma'am.
yes.
Hello, ma'am. There is one more question in the chat box that is,
Is it in a chat box?
yes.
Condition applicable before analysis only. Yes, yes. What is the question? We had used already available, but which question you are talking? I have answered 2 questions of Gajendra and 1 question of Alok.
Yeah, fine, fine. Okay, fine.
Okay. Well, let us open your workbench. Yeah. So now there are 2 ways of working onto your engineering data. Either you pick any of the simulation system and there will be engineering data into that, or you can just a second. Yeah, or you can just can you please enlighten us about the different Mooney Rayleigh material models if time allows? I'll try. Okay, so let us say if I open the static structural, there will be engineering data library available over here. And there is component systems. Okay, below that it's a component system. So if you really want to work on to the engineering data, so you can pick it from the component system as well. So as of now I will go through the engineering data. So just double click onto the engineering data. First try to understand, try to see. It's not nothing like understanding or there is nothing, I tell you, means it's very easy. Just see the GUI. Understanding the GUI is the very important thing. Fine. So let us open engineering data sources. So here you can see beside that you will see engineering data sources. So here you would be seeing different material libraries. Okay, so it has Ansys Granta material data. So this is one new thing Ansys have added in 2019. So Granta material is a huge material database library which will help you out for your simulation. Okay. Then there are different general materials. Additive manufacturing material library is given separate. Geomechanical materials are there, composite materials. General non-linear materials are there. Then explicit materials, hyperelastic, magnetic BH curve, thermal materials, and the fluid materials. So as per the problem you are solving it. So now this is a complete library. Whatever I have opened, engineering data sources. You can see here 3 books sign. Okay, it means it's a library. Okay, if you click onto that, it will take you to the library. Now just double click on general materials. So below that, I have double clicked on the general material. You will get a complete library of materials available under general material library. Okay. Then let us say I want to see composite materials. So if I click on composite material, you can see there are different carbon matrix and fiber properties are being given. Okay, it's not a huge library, but it is a basic material library you always use or you frequently use into that. Then you can see different explicit materials are there. Then general non-linear materials are there. So I will tell you how it works. Okay. Now let us say so let us say I'm working on some new material. Okay. But my material, or I want to generate my own material library. Okay. Now, please be means have your attention over here, because we are going to generate a new material library. So let us say I have some project, and I am working on some new material library. Okay. So now how to generate my own material library into Ansys itself, so that it will be handy for me whenever I am doing simulation. Okay. So you have to go to engineering data sources. You can see here different libraries you are used to of it. Now here below you can see click here to add a new library. Let us say my new library is ABC. Just here. So now you have to, so this whatever library you generate, it becomes a XML in .xml file format. Okay. So you can save it into your computer. Fine. So I'm just saving here. So ABC is my new material library. Okay. Now you can see here tick mark sign. Okay. So now in this library, I have to add a new material. Let us say XYZ is my new material. Let us say I have one more new material. Let us say LMN is my new material. So in this ABC library, I can have n number of materials. Okay. Now for this XYZ, let us say, or LMN, whichever I can take, I want to add properties. Okay, so whichever property you have whichever material library you are taking, you should have a property for that. Now see, once I click on element, in left hand side you can see physical properties. Let us say I want density. So for example, the density is 2700 kg per meter cube. You can play with the units as well. There are different unit systems are given on the beside. So you can just click on it. I'm going with this material. Now I'm done with one material. Now let us say I have to add, let us say my material is isotropic. Okay. So what material properties I need for isotropic elasticity? So whatever is in yellow bright color, that is a thing you must insert from your end. Okay. So let us say it is 2 e raised to power 5, and Poisson's ratio, let us say 0.3. You can take any values. Okay. I'm just taking as per my reference. So this is how you assign a new material, your element. Okay. Now let us, now I will take another material. Fine. Now let us say XYZ. Again, I will go to isotropic elasticity. Hmm. Okay, let us go to plasticity. Okay, so we will see what materials I can put here. So I will go with bilinear isotropic hardening. So it will ask me two things. One is a yield strength. What is the yield strength of steel? Anybody can tell me? Yield strength of steel. So you understood, first of all, tell me, have you understood how to create material?
Yes, ma'am.
Yes. So can you try doing this? I will show one more thing over here. Now this library, this is you have saved in your computer. You can mail it to mail. You can send mail to it is just a .xml file. So you can send it and you can save. You can see here. Yeah, import engineering data. If you have, let us say you and your friend, you are working on the same material library. Okay, so your friend can just mail this material library to you, and you can just import your engineering data over here, and even you can export it. So let us say I am exporting this, so you can export and you can save it. Okay, you can save this and you can send it to your friend. Okay, so can you now try generating a material of your choice? Related to tangent. Oh, good one. Material will help me out. Oh, good one. Visit this link. This will help you provide the things related to tangent. I thought you must be aware about the tangent modulus, secant modulus are there. Fine, no issues. You will learn in your consequent semesters. So now try generating a material library, and then we will solve a very the database, which there will be always a difference and there will be again new things will be there. Okay, who is sharing? Hello. Yeah. You know about physical properties, linear properties, right? You can add any value, or you can just take the material properties of whichever material you know, or you can just Google and you can try doing it. It's very important, okay? Because it will help you out going ahead whenever you are working on your projects and all. 6. सब लोग एक ब्लॉक क्रिएट कर सकते हैं, राइट? 30 by 30. Be specific in dimensions, okay? I'm specific about dimensions because if you take a higher dimensions, maybe you will get different results, okay? So that's why I have asked to create 30 mm by 30 mm by 30 mm. Done. Okay. Okay. So now this particular problem is all about the how linear properties and non-linear properties work. Okay. So be just look into it. I will give you time to solve it again. Just initially, I wanted you to generate that block. Okay. So now I clicked on the engineering data and whatever material. So whenever you solve any problem in Ansys workbench, specifically a structural analysis problem, by default, software will apply structural steel as a default material until and unless you go and change the material properties. Okay. So we will go with this. So now this is a general material property of structural steel. So you can check on the all the properties. Young's modulus is 2 10 to the power of 11 pascals, 0.3 of Parsons ratio, and here you can see stress life parameters, SN curve data. I mean general properties. Okay, you need not to worry. We won't need those things. You can see density of material and all things. Fine. Just I wanted you to have a check. Okay. Now I will open a model. Very easy problem. Nothing like that. Just understand the concepts. Okay. Okay, now you can see your block here. Now what we generally do, we apply some loads and the boundary conditions. Fine. So now what I will do, I will fix this side of my block. I will just add a fixed support. And here I will apply some force. Okay, I will apply a force. Let us say I'm applying 5 newtons of force. Okay. I'm just applying it in a vector quantity. You can, if you want upward direction force, you can do that, but I'm applying a compressive force into that. Okay. Now I am interested to know what is the equivalent stress. Okay. I want to tell you one more thing over here. Now you can see in the stress results, you can find equivalent von Mises, maximum principle, middle principle, different. These are all, what are these things? Can you, anybody can guess? Von Mises, maximal principle, maximum shear. What are these things?
Failure theories.
Exactly. These are all theories of failure. Okay. So your Ansys workbench or any of your software takes the reference of the theories of failure to predict the stresses or the strains. Okay. Since the structural steel is a ductile material, we are going with the equivalent von Mises theory. Okay. And now just solve. Now how much equivalent stress I have got? It's 449 how much it is? Can anybody convert it to MPa? How many MPa? 9 MPa. Okay. Now what is the yield strength? What is the yield point of your steel? What is the yield stress?
250 FE for
Yes, that is how much? 250 MPa.
250 MB.
Okay, but you are getting it 449. Okay, that is beyond yielding. So what graph software is following is a linear one. Okay, what material properties it is saying, it is just taking the linear material properties. So that's why if I, okay, I will just open my notepad, will not do. I will open my PPT again. So can you imagine what software is doing at the back end? It is taking it as a linear material. Okay. So what happening? What is happening? Beyond
Yeah, you can take
yielding
paint
also.
also. You can use
What?
paint.
Yeah,
can use.
I was just thinking of how to show it to them. Okay, so let us say, so this is your stress strain graph, right? So what software is doing? Yeah, I'm very bad in Paint, Tushar.
Just use sketching.
No issues. Let me try. I will be able to do it. Yeah, I am doing it. Fine. Okay, so now what software is doing? Can anybody guess? It is taking this as a linear one. Okay, this is, let us say this is your stress and this is your strain. Yeah, this is bad. Okay, this is your stress and strain. Just excuse me for this paint. Okay. Now what software is thinking? It is saying that everything is linear. Nothing non-linear happening, no yielding happening, no upper yield point, lower yield point, nothing. It is not showing. So it is saying that it will go in a linear manner and at some point it will break in a linear fashion itself. Okay, there is nothing happening in between. That's what the software is thinking now. So you are getting 449 MPa as a stress, but is it real? What do you think?
No.
You are making fool. You are making the software fool. It is giving you a right result. Okay, software is not committing any mistake. There is a mistake from your end that you understood this problem in a wrong aspect, and it will always indicate you. So, John, I just want to tell you one message. I want to tell you that don't merely be blind and just print the results. See whether is it true or not, whether it is feasible or not. Okay. Now what I will do, I will take the same model. Okay. I'm just taking the same geometry. Okay. I'm just sharing the geometry. You saw how I shared the geometry. You will do it. If you will miss it, I will tell you later. Fine. So now I will make it in here. Okay. Now what I will do, I will go to engineering data. I am having the same block. Okay. I'm not changing the geometry. I will go to engineering data sources. I will go to general nonlinear materials. Now go back and you see structural steel nonlinear. Here it is a plus sign. Okay. I will just added this to my model. Okay. Now I will go back and now open this model. Now I have the same block. Only one change I will do. I will change the material property. So you can go to geometry. You select your solid material assignment. You go to here assignment and here you can see one arrow. Okay. Now you just select structural steel nonlinear, which you had added previously into the engineering data. All other things I am going to keep same thing. Okay. I will apply a fixed support here. I will apply a force. I will apply 2e to the power of 5. 5 or 6 was there. E to the power of 5. Okay. Fine. Again, I will take stress and solve. How much you are getting now? 298. Is it nearly, is it now in your zone, visible zone? Isn't
Yes.
it?
Yes.
Yes.
around 250.
So this is the maximum of stress you are getting. Okay, maximum. You can see in the both results, that's the maximum stress you are getting. But here it was exceeding, it was almost double of your yield strength. Okay, so your results were not matching. Means your results were incorrect. So that's why I went back and just I changed the material property. Nothing else I did. You got it? Can you now relate your results whenever you will be solving your problem? Can you think of this aspect as well? Yes or no?
Yes, ma'am.
Yes. Many answers are there in Google. Okay. What is the yield strength? Or whatever material properties are also available. You have a huge database. I showed you the Granta material library is also there. You can take help of this. So there are different material libraries are available, but those are the inputs. But now what is the physics behind any problem that an engineer has to think of? Okay. Can you solve this problem now? Can you try it? I'm here only. Pre-stressed also been covered yesterday, parameterization, thermal, okay, everything you did, mostly thing. Now another thing which is very important is a transient structural analysis. So it is also called as a non-linear dynamic analysis. Okay, so there are different dynamic analysis. So your modal, harmonic, then random and seismic. These four type of dynamic analysis. I can show you over here. Modal, then harmonic, then random vibration, and then seismic analysis. That is a response spectrum. So these four are called as a linear dynamic analysis. Why? Because these are not dependent on time. So you know that equation of motion, right? Mx double dot plus cx dot plus kx. We saw it yesterday, right? Mx double dot plus cx dot plus kx is equal to f or 0. So whenever your force is function of time, then you are supposed to perform transient structural analysis. Okay, please understand, whenever force is function of time, then we are supposed to do transient structural analysis. And this is one of the dynamic analysis, and this is a non-linear dynamic analysis since your force is function of time. In other cases like harmonic, response spectrum, or random vibration analysis or modal analysis, your force is not dependent or it is not changing with respect to time. Your force is same. Okay, so this is one of the non-linear dynamic analysis, and in this particular analysis, transient structural analysis, all your structural non-linearities are being considered. Okay. Okay, so just let us start with that, how we can do this. So what I will do, I'm just clicking on the transient structural. Now I will import the geometry. So I have one caster test assembly I'm having. Let's check on the units. I will just open. Please see it very carefully, how any transient analysis is to be carried out. Okay. So can you see this assembly? Okay, so I will just once have a check on the units, degrees, because in the other simulations you have done, you were not more onto as checking on this degrees, radians, and all, right? You were just seeing this unit system, kg, and all. Okay. Now I want it is since it is a transient analysis, I will need it in angle should be in a degrees. Then rotational velocity I will be applying in rotations per minute. So I'm checking that, and temperature in Celsius. Temperature I won't need it here, but just I'm putting it as a Celsius. Okay. Now for this particular problem, what I'm showing you here, so you can see here there are two what I can say two strikers are there. Okay, these are nothing but a strikers, and now I for this particular simulation I don't need the upper striker, so I'm just suppressing that. So for my this particular simulation I will need only this one striker. This is not needed, so I will just suppress this body. So I have just suppressed this body. Fine. So now next what I am going to do is I have now this one body and this is one wheel I am having. Fine. Now you cannot see into the connections. These two bodies are there. Can you see this? But there is no contact is being assigned in between these two bodies. Since there is a small gap, there would be a small gap between these two bodies. That's why the contact is not assigned. But as soon as now see this is a transient analysis, I am going to drop this striker from particular velocity with some gravity onto this wheel. Okay, so so for that this striker and the wheel will be in contact with each other. So I need to apply a manual contact between these two bodies. Got it? So what I will do, I will go to connections, I will insert, I will here you can see manual contact region. Okay, so just right click and insert manual contact region between these two bodies. So now let us have, so my contact will be this surface. Okay, so this is my contact and this would be my target. So this one and this one is my target. You got it? Fine. So by default, it is applying a bonded contact, but I for this particular, I will be assigning a frictionless contact between these two body. Can you understand the behavior? It can get separated. Okay, frictionless contact, the behavior of the contact. Those two bodies should be in contact with each other, but at some point of time sliding will be happening, but at some point of time it may get separated. That is the behavior of the frictionless contact. That's why I have applied frictionless contact between these two bodies. Okay, now you can see this. Now other things now changes in case of the transient. Okay, now for doing a structural analysis, what you need to provide a support and you need to provide some load to your structure. Do you agree? Okay, now few things changes when you do a transient analysis, since your load is dependent on time. Okay, so now as usual, like we do a structural analysis, I will fix the bottom face of your wheel. I will right click and insert a fixed support here. Okay, now you can see still there is a question mark in front of the analysis settings. Okay, now what is being what is the tendency of this? I told you this striker is going, I'm going to drop this striker onto this wheel with some initial velocity. Okay, and for this wheel will be in contact with this striker. So now what I will be doing, I will be applying a frictionless support and at these three edges of this particular striker. Okay, I am applying a frictionless support on these three edges, because these three edges will be coming in contact with your wheel. Okay, once you drop it from some height. Okay, now here you can see that initial conditions are there. Okay, so you can see here, right click and insert. It's a velocity. So I need to add a standard earth gravity as well to my striker. Okay, just a second. It is being assigned to all bodies. So my striker is dropping with some velocity. So my initial velocity will be, initial condition is I have to give some initial velocity. But velocity when you will be going to apply, when you are having some, when you are giving some with some standard earth gravity. So what I will be adding here is a standard earth gravity. Now it will ask you for the direction. Okay, now can you guess, tell me in which direction I have to apply the standard earth gravity? Anybody can guess? Yes, who said X? He is right, it's a positive X direction. Okay, can you see? Okay, so now I have applied for the standard earth gravity in positive X direction. Now I have to apply the initial condition. So insert velocity. Now the geometry, to which geometry I have to apply the velocity, striker or wheel?
Striker.
Very good. It's on a striker. Okay. Now I'm going to apply 10 meter per second of initial velocity to it. Okay. I will do it 10 meters. Yeah, 10 meter per second. Okay, it's in a positive X direction. Fine. Now still you can see the question mark. Can you see? I still have to do some settings. I have to put some settings into the analysis systems. Okay. Now it is asking me number of steps. Let us say I will do it, one step only. You can add any number of steps. Okay, as per the your problem. But as of now, I am adding only one step and I am giving this current step is one only, and now I am changing the time. I will do it 0.001 second. I need it as it would be my end step. I'm just auto time stepping. I'm keeping on, or you can keep it off as well as per your problem. But for this particular problem, I need it as a time auto time stepping to happen. Now I have to define the initial time step. What would be the initial time of applying this initial velocity? Okay, so I will put it 0.0001. Okay. Now it is asking me what would be the minimum time step. Okay, so I will put it 3.5 and it will ask me for the maximum time step. So what would be the maximum time step? So I will put it as a 10 to the power e to the power of 10 minus 4. Okay, so this is what things we have to consider is this time check. It will be taking the additional calculations and the trial and error to find out this value. So whatever the values I have put, just I have done it by trial and error, and the what is the severe non-linear problem would happen, so that I have considered over here. And some things you have to consider, that whether this step and time is long enough to capture the full impact event, or the subsequent events or subsequent impacts are happening, so that you have to give the there should be some difference between your initial time step and the maximum time step. Okay, minimum and the maximum time step. So those things you have to consider. Okay, so now we are done with initial conditions. We have done settings in the analysis settings. We have given standard earth gravity. We have applied enough supports. Okay, now I will just solve this problem. See, here you can see large deformation effects are active, means large deformations is likely to happen during this solution. Okay. Now let us say I will see the deformation, total deformation. Just solve it. See, which may have invalidated some of your applications. Okay, so total deformation I am getting this. Now I will show you the results. Okay, now here it is getting an auto scale. Okay, I will make it to a true scale because you will be able to see the difference. Okay, I will show you here. You can see how it is happening. Can you see this? Okay, number of steps I will definitely tell you. You got it? So now number of steps, someone has asked me what is the why we need a number of steps. Okay, now let us say sometimes what happens, we apply a force. Okay, let us say I'm applying a 10 Newton of force in one stroke, in a time interval of 0 to 1 second, let us say. Okay, so it will apply the force from 0 to 0 second to 1 slope in just one stroke. Okay, now what happens if we increase the number of steps is it will apply that force into number of, there are different types of steps. Okay, there are the load steps and there are the time steps. Load steps mean I can divide my load into n numbers. Okay, that is called as a load steps. And time is the same force I can apply in the different intervals of time. Okay, so uh, the problems like this, whenever you are working on some transient problems where your force is dependent on time, you have to increase the time steps. Here you can see steps and end time. You have to divide, let us say the interval of 0 to 1 second. You have to divide that time interval into number of steps. Okay, maybe two intervals, that is 0 to 0.5 seconds and 0.5 to 1 second. Or you can further go ahead and divide it into 10 steps. Okay. Any queries? Can you solve this? I have shared the file into that shared folder. I will tell you the name of the file. It's a caster underscore test. Caster underscore test 2. You can see my screen. If someone is failing to assign the contact region, what I did, I right click and insert the manual contact region. Okay. So this is your contact surface, your contact body, and these two surfaces are your target bodies.
Hello, ma'am.
Yes.
Ma'am, on which surface we have to apply frictionless support?
Frictionless support. Okay. See, this surface, this, and this one. These three is a frictionless support. To assign standard gravity. Okay, no issues. Okay, you go to transient. Okay, right click and insert. You can select body, right click and insert a standard earth gravity. Okay, you have to just transient, right click and standard earth gravity. Okay, I have already applied it, that's why it's not showing, but you have to apply it on a body. Okay, very good. Who is this? 10 meter per second. Okay, you go to components and you add it to positive x direction. Where is defined by, you make it components. Okay, below that defined by vector, it is there. You click on a vector, yeah, and make it component and make it positive x direction 10 meter per second. Very good. How to provide direction of velocity. I have just opened the analysis settings for your reference.
Yes, yes.
Can we have limited
Meanwhile,
vacancy?
you can. Okay, there is one query.
Mooney-Rivlin
We
model,
have
yeah,
limited
Mooney-Rivlin model. I will share some document with you. Tushar, they wanted to know about these material models. Okay, I was just
Okay.
talking about different material models. In that, Gajendra wants some information on Mooney-Rivlin model. So Gajendra, I will
Gajendra,
share.
Gajendra,
Yeah.
what you can do is in a feedback itself, what we will be sharing just in a few minutes of time, you specifically mention your query there itself. Okay, and based on it, we will get back to you. Okay.